post. I made an announcement in there so that people would see that, but you have to go to the first post to find the code.
Yeah, I'm looking at the end. That's why I can't find it.
Sorry, should have told you that.
Let me go. Let me go, nerd.
Well, welcome everybody. Let's get started. A lot of familiar faces here and a lot of new ones too. This is going to be a lot of fun. We gave Chip the day off today, and we're very fortunate to have John's attention to start us out with the project. If you're just showing up and you're a little confused about what's going on, or you're watching the video out of order or something, that's fine. What we're doing is we're using this pile of parts called the P2 Lifeform Holiday Spin Toolkit, and the parts are all available on Amazon as well. There are links on the product page on our website at Parallax, and we're going to start out programming today with John under his direction. And the drivers for this are, the ones we're using today are available on the forum thread. Somebody will grab it and paste it into the chat for us, hopefully. It's important to me that we support JonnyMac, and I have gone over there today and made a deposit in the JonnyMac account to show our appreciation for him. And I don't ask for John's permission to do this, but I think it's very important because so many people, I talk to a lot of customers and they all benefit from his code, and a lot of it is used in commercial applications where he gets no benefit. And Parallax is a tremendous benefactor as well because he's produced most all of the objects for the P2, and we're really trying to keep him going. And he has been a big part of Parallax's success in the past, with a number of products and things like StampWorks and the code that's gone into that kit, and about 50 million other lines of code that people have used. So there are several out there in his club. You know, many of them are hanging around here on our P2 Lifeform at the moment and contribute as well, and we're very thankful for this. So I'll post a link to his checkout line, which is a safe place to leave your credit card behind in a little bit. So I think I will pass this over to JonnyMac, live from Hollywood, California.
Thank you, Ken, and thank you as always for your friendship and generosity. You're always very kind to me. I appreciate it. Okay, hello everybody. I know quite a lot of people, but I see a lady named Jean R. I don't know Jean, so hello Jean.
So quick comment, if I can interrupt just for a moment. So yeah. That's actually a 10-year-old boy.
Oh, I'm sorry.
Yeah,
I saw the lady and I saw Jean and I thought, oh, I'm sorry, is that Jean?
Well, the important part of this is,
forgive me,
this is a student that was handed a robot kit 3 years ago by somebody who had attended Parallax seminars for teachers. And this young student, I think his name is, well, he can say his name since he's under 18, but he started learning things and hooked up infrared emitters and ultrasonic sensors and posted his videos on YouTube. But yeah, the importance of this is it's a result, his success is a result of sharing. So somebody gave him a robot, you know, in the same way John is giving us his time today. That's our job. Share with somebody else, share with the student or whatever. So welcome, Gene's son. And you are seeing today a very new high-tech processor. And some of this you might understand, you might not, you might understand better than us, but I say take it all in. You're working with engineers and hobbyists, and they're doing cool stuff with the Multicore Microcontroller. That's all I want to say, John. Thanks.
Okay.
Back at you.
All right. Sorry about the mistake, but welcome and well done with the robots. I see my friend John Hoffman. We were just speaking yesterday. So this is really fun. You know, it's been crazy here in California. So David, are you going to have to look through your cat's tail the whole time? This is kind of fun being able to look at people and see what's going on. No, you didn't have to move the cat. I was just wondering. Cats always do that, right? At any rate, you know, those of us in California have been hit particularly hard with rules vis-a-vis COVID. and it's been a little tough. You know, I'm a quiet guy. So for those of you who don't know me, I guess I should introduce myself properly. My name is John McPhalen. I do live and work in Hollywood, but I actually live on the other side of that hill. This is a fake. There's a green screen, and I'm actually on the other side of that hill right now. That's where Burbank is, where I live right around the corner from Disney Studio and Warner Brothers Studio, and lots of crazy stuff going on. They shoot movies and TV in my neighborhood, and I do a little bit of work in that business. So I'm going to show you some pictures from that. I'm a technical guy and a part-time actor, and been associated with Parallax since 1994. When I finally bought a basic stamp, I saw the basic stamp in 1993 and thought it was nonsense, because I live in Los Angeles. We don't believe anything until it's proved to us. And when I saw the ads for the basic stamp, I thought, no. And then I had this opportunity for some downtime, and I bought one. And I stayed up all night playing with it, and there's not been a day since that night in 1994 that I haven't written code for a Parallax processor. So I've been through the gamut: the basic stamp 1, the basic stamp 2, the what am I trying to say? The Java stamp a little bit, you know, the SX. I worked with some of the old timers in the forum know Terry Hitt, who goes by Bean in the forums. He created a neat little compiler for the SX called SXB. I helped him with that. And then the Propeller came out, and I really lost my mind. The Propeller speaks to me. So if I seem to go into a trance, just forgive me. I love everything about the Propeller. It works for me. And so all of my coding is around the Propeller now. I occasionally write stuff for other processors, and even in basic stamps from time to time I help people with, but I love the Propeller. And the P2 really makes me happy. So today we're going to start very easy, but at the end, if you've got the stuff in front of you, if you acquire it really quickly, you'll be able to make, you know, Ken had some blinky lights set up. Those are these smart Christmas. Oh, you can't really see them with my green screen. But you'll be able to run them. And importantly, you'll understand how they work and how you can change the code the way that you want. One of my real frustrations with the kind of the current state of microcontroller training is that a lot of people assume you don't want to know what's underneath or how things actually work. You just want it to work. I think this crowd is different. Now, maybe there are people that just want it to work and don't care how it works, but I think we're different. And so I'm going to share with you how the thing works. And we're not going to get into gory detail, but enough that you can play when you want to. That's one of the things that I also really like about the Propeller architecture, is that if I or any of my colleagues that I see on screen, if we write an object and share it with you, you can very easily look at the code for that object and change it if you like. That's a little harder to do with a lot of other products that are available today. So is there any questions before we start? And please feel free to interrupt. This is, it's a couple of days before Christmas. We just finished Hanukkah. We're in the holiday spirit. So let's make this really easy and fun. I'm doing this to share a bit of information with you, and I'm open to anything that you want. So questions,
What we can
just
do
shout them out.
is take the roast beef, heat it. We could have
Okay, so I'm muted.
Okay, I guess
Anyone's
that
welcome.
was not for us.
Anyone's welcome to shout out a question. This is totally open. Otherwise, just keep yourself muted so you can eat dinner or wrestle with your cat or whatever.
So can I share my screen?
Yeah.
Ken?
Yep. Over to you, John.
All right. I want to share my whole screen so I can go between applications. So I need to share screen, right?
Display, yeah, or screen as they call it.
Okay. All right. Hopefully you see my, do you see my PowerPoint?
Yes.
Oh, you
We do.
You do?
Yeah.
Okay, good. All right. Let me.
And it looks like you're sharing more application than screen.
Oh, really?
Yeah.
Well, it says I am screen sharing.
Okay.
So I have it wide. So we'll go through this because I'd like to be able to go back and forth between things if I can. And I'm not going to bother trying to expand this and hide the previous slides. We'll just go through. So we're talking about today, we're going to do programming in Spin, some fairly simple stuff. But the great thing about Spin is it's fairly simple and you can learn it in just a day or so. And again, I'm John McPhalen. My hacker handle is JonnyMac. You may call me John or JonnyMac. If you call me Johnny, I will pretend I'm deaf and not hear you. Okay, so this is me really quickly. I was born right that way, and that's downtown, that direction. I was born in downtown Los Angeles. So I'm a native of Los Angeles, which is a little unusual for people in show business. I have my technical training in electronics from the United States Air Force. I have 3 patents, 2 for a sprinkler timer I designed for Toro and 1 for a water intake system that I was part of a team, which was a little unusual, but I had a wacky idea and it was patentable. I am a part-time actor and sometimes get paid for it, so I'm a member of SAG-AFTRA. In addition to coding, I do a bit of technical writing. I write a lot for Nuts and Bolts magazine. I have in the past, and I've started again. Their current printed issue has my P2 introductory article. As Ken mentioned earlier, I wrote a book called Stampworks that went along with a kit that was quite popular back then. And as I told you, I've been using Parallax microcontrollers since 1994. These are some of the things that I've done, commercial things. A product called Hotwire for Flowtronics PSI was a water pumping company. This was an alarm device. This was back before cell phone days, so we actually used an embedded modem and we would dial out to a pager system and put codes on pagers like hospital codes. I've done lots of controllers that are used in movies, TV, Halloween, escape rooms, etc. A lot of those designs that I've done are built by a company called EFX Tech, which is owned by another former Parallax employee. I created a networked HVAC controller for a company called Rocky Research. That was quite interesting. It was a really big project that ended up going really, really well. You know, some of this stuff is not sexy or, you know, it's very mundane, but, you know, you drive down the road, you see the big signs where they go clunk, clunk, clunk with the big arrows on them. Those are called arrow boards. And there's a company in North Carolina now making them with propellers. One of my companies that I've worked with called Elite Laser Tag, they make laser equipment, laser tag equipment. They have a propeller-based controller and lots of propeller-based accessories. I've done some camera platform controls and lens controls for my friend John Huffman of Johnny Jib, makes great products, and a former friend of ours who sadly is in heaven now, a guy named Lou, who had a company called Camera Turret. But those are always very fun, and John and I are currently working on another project. What happens here in Hollywood for me, we're all kind of specialists and part-time employees. So I do lots of little specialty things, and I'm going to show you a few of those for TV shows and et cetera. And then lots of stuff for trade shows in the gaming industry and other places. Here's one of those trade show displays. Some of you have seen this. This is for Riot Games. These are these characters, Annie and Tibbers. So this is a pretty large display. This bear is 8 feet tall. And believe it or not, one propeller runs this entire display. The way that it does that is it's a DMX controller. And on this display are 4 trees, this bear, and this little girl. Now, the little girl only has one lighting channel. It's in her palm. And so she shares a channel with this. And it's all fire simulation. But the way that I did this that is really easy to do with the propeller is I broke the project into pieces. So each tree has its animation running in its own processor, the same for Annie and Tibbers. And then there is a DMX processor that is streaming out the DMX data. Now, DMX is a very easy byte-oriented protocol, but it's constantly streaming out. That's interesting because these lights that we're playing with today, the driver does the same thing. It's constantly streaming out the data. So when we understand that, we can use this information to manipulate the data in such ways to get advanced animations. I don't know if he's online, but I have a good friend named Matt who does amazing stuff with my Pixel driver that we're going to be playing with today. This is a character from a TV show. The character is called Thunder, and her belt buckle was made originally kind of quickly and by hand by somebody, and it broke on set, and it was a real problem. So the company that made the costume hired Rick Gallinson, whom many of you know. He's the guy that made the propeller-powered Gatling gun that shoots paintballs. And he came in, measured everything, got the original artwork, and he made a 3D model. And then he sent me the PCB requirements as far as the shape. I designed a PCB. This is the model output from DipTrace. And we were using, now these are smart LEDs. Now these are not the kind we're going to use today. These are another kind, but they're smart LEDs nonetheless. So we designed this overnight, sent the board out, and got it back. And it worked so well that they said, oh, good, change the controller too. The original controller in the costume was run by an Arduino Mini, so we replaced it with a Propeller Mini. Now, forgive me that this code is, or this photo rather, is a little on the blurry side. But we didn't have time to send out for a PCB, so I have a mechanism for hand etching PCBs, and I did that. We were able to pull this off as a single-sided board. And the only thing that's on there, honestly, is the Propeller Mini, a few resistors for pulling up the output from a wireless DMX receiver, and then a chip called a TC4427, which I use to bump the 3.3 voltage, the signal voltage out of the propeller to 5 volts to go to the APA 102Cs, which are the smart pixels used on that. In the end, we also, because of the propeller's capability, instead of just monitoring one DMX channel like the Arduino did, we actually monitored 4, although we only ended up using 3. But the point is, with fairly straightforward code, we were able to give the lighting people more control. It was not just animation, but we gave them smoother animation. And we also gave them the ability to set fine brightness and coarse brightness, which they didn't have before. And in movies and TV, lighting is everything. So that was a big help, and that was it was a rushed project. This was Christmas 3 years ago. We did this. We had to turn this around in about a week and a half and get everything back to Atlanta so they could start shooting again. And it worked, and it was great. This is another little mini trade show demo, and these are using the same driver that we're going to be playing with today, most of us. These are bulbs from this company called HolidayCoro.com. And the genesis of this project was Matt, my friend that I was just telling you about. He turned his house into Stranger Things set and had a full-size wall with the lettering and everything on there. In fact, he sent his graphic to me, and I miniaturized it and adjusted it like this. And these Christmas bulbs, these are C9's Christmas bulbs that are fine for outdoor use, and they're run with 12 volts instead of 5, so they can be quite bright. But they're controlled by this propeller board over here. And what I did with this was I attached a little Bluetooth radio to the propeller, and then I made a simple terminal app for my phone. So I could change the colors or re-randomize the things, and then, but I could also spell out a person's name. So if you've seen the show, there's one of the main characters, her son is trapped in this weird different dimension, and he's able to communicate her by dimming light bulbs that are associated with letters. And that's what we did here. So at the trade shows, I could say, hey, what's your name? And I could put it into my phone, and then this sign would spell it out. And people thought that was really quite neat. So these bulbs are from Holiday Coro for those, yeah, it's a little late for Christmas this year, but next year, Holiday Coro makes these bulbs and it will work with the driver we're using today. I mentioned my friend Rick. We've done that, the Thunder thing. This is a commercial that he did. So there's lots of propeller powered stuff in here. Hopefully this will show. Let me know if you're seeing the video.
Yep, it works, John. If there's any audio, I don't think it'll come through, but you could talk
No
us through it.
audio?
Right, and that might be somewhere on my side. Some advanced setting.
I can hear it, Ken.
Yeah, I don't think the others can.
Yeah, we can't hear it.
Yeah, John, we've got video, but no sound.
Okay. This is really about the video. So what I'll do is I'll just skip along to where it's important. Well, Rick built this guy's mask and used a propeller to control some servos and the lights in there. But also, let me get to the other characters. Right. These guys here. So these actors are all carrying props. You can see they're all nicely lit up and they got all this crazy stuff. These all have propellers in them that are animating the lighting on these props that provides a guide for the animators, because you can see there's fire on this. Well, obviously there's no fire on set. There was just animated LEDs. But in our business, we have this thing called practical lighting. So for example, I have this desk lamp. If I turn it on me, then you can see the light on my face. We call that practical lighting. So Rick made these props, so he put practical lighting that was also then used by the animators to do the enhancements. So the practical lighting shines light onto the actors, and then, you know, so that's one part of the visual, and then the other is a guide for the animators to do that. So you get a much better look. So those of us, you know, if you're my age, you remember the original Star Wars, people would wave around lightsabers that were emitting light, but not casting light on anybody's face. We now are better at that, and we know how to do it. Because animating light onto a human is really hard. It's better to use practical light, and so that's what Rick did. He, you know, he's using my pixel driver and WS2812s in this particular case to do that. Here's one final project that Rick did also with the same pixel driver. This is a commercial from South America. And what is happening here is these, I'm gonna skip ahead. These guys decide to make suits with pixels on them and then go snowboarding. So the crazy thing about this is there's 2,000 pixels on every suit. And each actor or actor slash snowboarder had a guy on a radio control controlling his lighting. There's a big thing that they do in the business is they use radio controls to control that. In fact, one of the projects that I have coming up for Rick is to write a P2 driver to read the pulse data out of a RC receiver so that he can do something with it and control lights or send it to other servos. Or he's doing a lot of work with Dynamixels now too, but he still wants to use a radio receiver. In the P1, it's not too hard to read pulses, but it's much easier in the P2. With smart pins, I think I'll be able to do it in just a few lines of code. Okay, any questions? So the reason for the little show and tell is that we're actually using the propeller in real world stuff in Hollywood. There's all the smoke and mirrors, a lot of it we control, and we can do it. And this stuff, you know, we have to do quickly and reliably. And that's one of the great things about the propeller and programming in Spin is it's a very easy language to learn, but it's a very efficient language and a very capable language, and you can turn around and make changes very quickly. I was telling you about the Annie and Tibbers thing where I made each of the trees and the bear and Annie all separate processors, and I did that because my client, a guy named Steve, he often says, okay, John, just turn on that tree. I only want to see that tree, turn off everything else. Well, since everything's running in their own cog, that becomes quite easy. I just don't start up the other cogs. I have the DMX cog running and I turn on that tree cog, and then we can fine tune its animation. And when he's happy with that, we do the next tree and the next tree and the next tree, then Annie and Tibbers, and we're done. So the Propeller, because of its unique architecture, really is beneficial to the way we do artistic technical projects, because they're always on ridiculous deadlines.
John, you also, your driver was featured in a Super Bowl commercial for
Oh,
his
yeah,
giant
that was
Pac-Man, which
yeah, that was another Rick project. Yep.
a very notable use of it.
Yep. Yeah, that was a Super Bowl. What are they? The halftime commercial. So that's big exposure. That used the pixel driver as well. And if you look very closely from the overhead shot, that the camera's looking down, you can see Rick hiding in the maze, running the Pac-Man. All right. Okay. Here's my approach to programming, and I say it's my approach. This is every professional's approach, I think, but there's a little bit of my Californianness built into this. Know where you want to go before you start. That generally helps. Something I often say to people is, hey, the root word of specification is specific. Know specifically what you want, because your specification is kind of like GPS. If you get off track, if you just go back to the specification and say, okay, that's what I want, and you get there. Now, it's not always easy. Sometimes things take longer than others. I have this amazing friend and client who's being very patient with me right now because I've struggled a bit with a project, but we will get there because we know what we want. You don't have to know a lot of stuff, but you got to be comfortable with fundamentals. And for me, that's being happy about playing with numbers, and binary and hex in particular, for all programmers, but I think embedded programmers in particular. One of the fun things I did, I used to work for a company that was a cybersecurity company, and I taught programming and would often do little, seminars on numbers. And the next day I would come in, kind of shout out, okay, so-and-so, if I give you this decimal number, what is it in binary? What is it in hex? To kind of keep people thinking about that all the time. Rick and I always laugh when we're out. If we see a street address that is just ones and zeros, we'll shout it out as its decimal equivalent. My physical address is 1111. I always say 15 as a joke. People that understand binary will get that. Then logic is the other thing you have to embrace, because a program is really putting your logic into code. You're making decisions, and that's all about logic. The core of all logic are these three fundamentals called and, or, and not. And if you go back online and look at my other presentation, I go into a lot of detail into these, so you can pick that up there. There's another or called exclusive or that is also really important, and down the line you'll see that in play. Now, if you're new to all of this, if you're new to programming in general or new to the P2 specifically, just love learning, because it's fun, and the P2 is really fun. And if you have a love of learning, then even the hard projects, or where you're stuck, or things are frustrating, they ultimately become fun. So love to learn and be willing to experiment. One of the nicest compliments I got was from my friend Matt, and he said to me one day, I don't understand how you think. I need something and you give me the code, and I would have never thought of it. And chances are it's because I do so much experimenting that it's just one of the things that I came up with and I kind of put away in my bag of tricks. So if anything, for those of you that are, going to play with the P2 or any processor, whatever it happens to be, give yourself a little bit of time each day to play and experiment. It'll all stack up and be so helpful down the line. Okay. Since there's a bunch of people from the Propeller world here, I thought I'd just do a really quick kind of difference between P1 and P2. Max speeds, max comfortable speeds, I'm going to say, P1 100 megahertz. I've done that a few times, no problem. You have to have an odd numbered crystal, but I think Parallax still carries them. Do you, Ken? The 6.25s?
Yes, we do, John.
Okay. Yeah. So if you, yeah, because on the P1, you have a PLL circuit that multiplies the incoming crystal by 2, 4, 8, or 16. So if you multiply 6.25 by 16, you get 100 megahertz, and that's a nice frequency to run. The P2, quite a lot faster. You can go up to 300 megahertz comfortably. Now, I know a couple of the other folks online that, they're saying, well, you can go faster than that. Yes, you can. But I'm saying comfortably, and, where you have environmental considerations. You had no problems with these numbers. Both have 8 cogs. Difference obviously in memory. So the P1 had 32K of hub RAM. The P1 had 32K. The P2 512K. And it's a lot more space. On the P1 we use an EEPROM for storage. On the P2 we use flash. So the reason for that is because it's big, and the flash is really fast. For those of you that, if you haven't yet had the opportunity to try the P2, you'll be shocked how fast it can download and program the flash, versus the EEPROM on the P1 is fast. When I'm playing with one of those other processors, I'm thinking, jumping Jiminy, this is taking forever to compile and download. Why? Because a Propeller is so fast. The P2 is it's instant, and it has programmed and download and burn the code into flash. It's really, really fast.
Sometimes I hit that button over and over because I just didn't see the progress bar.
You think, wait, did that actually happen?
Am I connected?
Exactly.
Is it powered? Is the cable there?
Yes. Yeah, I almost think Jeff ought to put an arbitrary delay into the screen so that you actually can see it.
Yep.
Because it is that fast at times. And I have a very fast computer, so things just blow right through. The cog RAM in the P1 was 2K. And in the P2, it's 2K plus 2K, but yes, it is kind of 4K, for the really advanced users who know how to manipulate that. And that's really helpful. You'll see, for those of you coming from the P1, there are a lot more features in spin in the P2 because there's more room in the cog for code. The other interesting thing that the P2 can do is run code from the hub. In the P1, some of you will remember there's a guy in Canada named Bill who created this thing called LMM, which was in effect an assembly interpreter. That's kind of a weird thing to say, but what it would do is it would pick out assembly code from the hub and run it and then do that again. So you got faster code execution than spin, but not nearly as fast as raw assembly. And now with the architecture of the P2, you can run full speed assembly out of the hub, unless I'm mistaken. And if I am, somebody correct me, please. But I think you're running full speed assembly out of the hub, which means you can have giant assembly programs, which is really good for those that are writing compilers.
Yeah, it is full speed, and
It is,
the only hit is when you do a branch, it has a extra stall because it has to refill the FIFO buffer.
Okay.
So branching is slower, but serial running of PASM is full speed.
Okay. Thank you, Roy.
Does that, John, bypass the 12 clock ticks for the access, or is that taking that into consideration as well?
I don't know. I'm going to ask Roy to answer that.
When you branch, that extra clock hit happens, but when you're just running serially after it's primed,
No.
you're running at full speed as if it were in cog memory. When you
Okay.
branch,
All of you.
what was that?
Yep.
Got it?
Okay, cool. Thank you, guys. I/O pins, another big expansion here. On the P1, we had 32 physical pins, although, I put an asterisk there because I always treated it like a 28-pin processor with a debug and programming port and an I2C port. on the P2, I do the same thing. I treat it like a 56 pin processor, at least with the current boards. And because you have 2 pins that are used for the serial programming and debug, you have 4 pins that are used for the flash. There are 2 other pins, 55 and 50, or 56 and 57, I think they are. But they connect to LEDs on the edge and on the demo board, and you can't really use them for other things unless they're driven signals. So I don't count those. And I was just trying that today. You'll see a picture. I'll show you what I was talking about. But still, it's 56 IOs. It's a lot of IOs, especially since you have now analog input and output capability, and in particular, smart pins, where in many cases, things that we would have to do in a cog before, we can now set up a smart pin to do that. And, you know, I was mentioning my friend John, who's online with us, you know, we do these camera control things. And there was a project that we worked with our friend where it had, you know, 2 different cogs dealing with rotary encoders, and then 2 other cogs for motor controllers. And in the P2, those can be replaced with smart pins. So we free up 4 cogs from that project by using smart pins. So they're, you know, it's not the answer for everything, but for a lot of things, it's really good. What I was just saying is I've started looking into doing pulse inputs with a group of smart pins so that I could read a RC radio receiver for Rick. And I'm pretty sure that once the smart pins are set up, it does take a little bit of code to set up the smart pins. Usually not too much, but sometimes there's a bit. And so you weigh that. So for example, to be honest with you, I was trying to do SPI with smart pins. For the new people, SPI is serial peripheral interface. So it's a type of communications. And I just found in the end that it was easier to bit bang it in assembly. And in fact, I had a little bit of an exchange over the weekend with Mike Green, and he had been using one of my early SPI objects that was using the smart pins. And so then I sent him my assembly routines, and a few minutes later, I got an email from him saying, hey, that works. So that was really good news because Mike's working on some flash access stuff. So that's really happy news for everybody. So, you know, this is where the experimenting comes in. You know, you give it a try, and sometimes you say, okay, I could do it with smart pins, but actually it's just easier to do it this other way. And because of another feature in the Propeller, which I'll get to in the Propeller 2, even if you want to do assembly, you don't have to run a cog, and I'll explain that in just a minute. So from Parallax, I should say I was trying to keep my slides down. I'm already looking at the clock and seeing how long I'm going. But on the P2 from Parallax, you can get it in this form, which is the P2 eval board. And then the other version is this cute little dude right here, the P2 Edge. And for those who haven't physically seen it, this is only about 2 inches across and about 1.25 inches tall or so. So it's quite small. And this is a nice board because it's got the P2 and all the power supply decoupling. It's a little tricky to see, but on this board, there are the 3.3 volt power supplies for all the IO pins. This is the 1.8 volt power supply for the core logic. And then here's a 16 megabyte flash. So we're using half of a megabyte for the program storage. The rest is available for us. That's why that stuff that Mike Green was working on made me happy, because maybe it'll give us easy access to that. And then there's a couple little configuration things here and a couple of LEDs, which we'll play with today for those of you who are using the P2 Edge. Now, because it has a finger edge and it has to plug into something, here you can see it plugged into this, it's called the P2 Edge breakout board, or it's affectionately or infamously called the JonnyMac, because I suggested it to Parallax and then they turned around and did an amazing job with it. And here's the one, this is the one on my bench. You know, this is the one that's sitting right in front of me now, with the stuff that we'll deal with next week or the week after. I've got some I2C stuff plugged in, but here you can see you've got a very large breadboard area. You have all of the connectors, and what I like in particular is you have the male connectors that are compatible with the things like, hopefully this will show up, the accessory boards that go into the eval, they'll work on here as well. And then you have female sockets as well. So, oops, I screwed up my slide. So you can see I'm going from this LCD is I2C based. This is a real-time clock module with an EEPROM on it. And so they're all connected to the same 2 pins. And if you run a little I2C scanner, which I will give to everybody for the next, when we deal with this stuff, you'll see all of the addresses for this. It's really a great board. This is the prop plug, plugs in. Here's power. This is 5 volts on the board, so be careful about that. You know, a lot of us are used to plugging in 12 volts. This is 5 volts. So on my board, I don't know if it'll show up, but I actually put a sticker on my connector that says 5 so that I don't plug one of my 12 volt supplies into the board. But it's quite nice, and I'm honored that my friends at Parallax put my name on it. So some of you have probably seen this, but if you want my autograph, buy a JonnyMac board, and then you can have a great experimenting tool and my autograph. Okay, I know you don't want that latter part, I'm joking. All right, here we go. With the propeller, remember I was telling you we have 8 cogs. They all run simultaneously. There have been people out in the world saying, oh no, it only runs one at a time. That's nonsense. They all run simultaneously. In the P1, only one cog could talk to the hub at the same time. So that's what got people confused. But technically, all of the cogs in the P1 and the P2, they're all running simultaneously. And they're all simultaneously connected to power and reset, the IO pins, and to the system counter. Now, in the P1, the system counter is 32 bits. In the P2, the system counter is 64 bits. So for those that are new to the propeller world and thinking, wait, all of the IOs are connected together? Yes, they are, but not directly. So you don't have an output from one processor going to an output of another processor and causing a short circuit. They're all ORed together so that they all play nicely with each other. But because they are ORed together, if any processor makes a pin an output in high, that pin's going to be an output in high. It doesn't matter what any of the other pins are doing. So sometimes you can use this to your advantage. The cogs run propeller assembly 2, PASM 2. And in our case, that's going to be the spin interpreter, or it could be your custom code. And I'll show you, we're actually doing both in what we're doing today, because the main code we're going to play with is running in spin. The driver code for the pixels is assembly. And so we're doing both things. There is round robin access to the hub. And what I should clarify is in the P2, this is to a specific address because all cogs have access to the RAM at the same time. And there's a neat trick that adjacent cogs can share data through their LUTs. That's a really advanced thing, so we're not going to say any more on that. And as I mentioned earlier, a cog can run code right out of the hub. That's called hub exec. Here is an update of an image that I had done before. This kind of shows the architecture in a kind of California, graphic. I don't know. It's an airy-fairy. So these are the cogs, 0 through 7, and you see they're connected to the I/O pins and the system counter. And this dark gray area is the hub, and these fingers are access to the RAM. And in the P2, what's unique is that the RAM is divided into 8 slabs, and each slab is controlled by the lower 3 bits of its address. So once a cog is aligned with the address it wants, from that point forward, it's in sync. And so every cycle, it can read or write. And so this makes the P2s amazingly fast. And one of the things that you see for those of you coming from the P1 to the P2 the first time, you'll say, wow, this runs fast. A lot of it has to do with the internal architecture of moving between the hub and the cog. It's crazy fast. There's a popular forum member who goes by Ariba. His name is Andy Schenk, and he speculated that P2 spin probably runs nearly as fast as P1 assembly. And it is really fast. Now, some of that too is the P1 uses 4 clocks per instruction. The P2 only requires 2. So you're running 2.5 times as fast if you're 300 megahertz versus 80 megahertz, which is the typical, 200. I use 200 as my standard, so I'm going to use those numbers. 200 megahertz versus 80 megahertz, so that's already faster. And then you double that again because there's only 2 instruction cycles, 2 clocks per instruction versus 4 with the P1. So it's just, you know, in the end, these are details that we can put aside, but it just makes an amazing experience because the thing runs so fast and we can get so much done in so little time. So as I was saying earlier, I'm going to be running Propeller tool 2.4.1. If you haven't installed it, please do. You don't have to do anything special like I suggested you do in the past because the library folder, which is what's critical for us, now is in a user location. So, and you'll want to know where that is. So if you go to your documents folder, you'll find Propeller tool and library. So those of you who downloaded the files for today, there is a file, there's a folder in there called library. Copy those files into this folder and then you'll be set. And if it says they're already there, just overwrite them. That way you have the latest version of what I've written. So it is a Windows program. Parallax is you know, still for the time being Windows centric. But I've seen Propeller tool run fine on Macs in many instances. As I was saying, I make heavy use of PST, so I apologize for the slight discomfort this might cause the Flex Prop people, but we'll figure that out down the line. Okay. Any questions so far? I'm doing all the talking. Going.
I posted a link to the code, John.
Okay, good. All right, so getting up and going, I tend to do the same things over and over again. They mostly work, so I'm going to share them with you. Start with a template. That will simplify things so much from the jump. And in the files that you got in that library folder is a file called P2 template. And you can assign it. So if you go into Propeller tool, can you see my Propeller tool?
Yep.
Okay. If you go into the preferences dialog and then on files and folder, right here, you can set your templates for the P1 and the P2. So you can set that up. So for example, if here's the one I saved. Let me close that. If I say new from P2 template, I get a new file that has all my basic stuff built in. And it's a nice clean framework that I can start with and build on. So I've included mine. I would suggest you start with that. And as you become more experienced, you'll figure out what works best for you. And then you can create your own template. But start here to begin with. It'll get you going really cleanly and easily.
And it looks like the default for preferences, files, and folders goes to the templates already, which is nice.
Oh, yeah, it probably does. I have an older setup, so I may not have seen that. So, you know, use templates. When you get started, remember I said, you know where you want to go. So one of the things you'll do, and for those of you new to all this, some of these terms will make a little bit better sense after today, but you can populate your program with empty methods. So let's say you have to, in the course of your program, have a thing that checks a button. So you might just put pub space check button, parentheses, close parentheses. And then, you know, that's it. That's all it has to do. It's an empty thing. That way you can call it. So build a skeleton program and then go fill in the code. And as you fill in the code within each method, you know, develop those and test them independently. So you make sure that a method is working before you move on to the next. Now, this is not always possible. Sometimes dependencies will cause you to do 2 things at once. but to the degree you can, develop a method, make sure it's working, then move on to the next. That way you don't get to the end of a giant slug of work and nothing works and you're not sure where that's broken. It'll just make things a little easier. Now, I'm a bit of a maniac. My desk, not so neat. My code, very neat. So I will say, keep your code neat and tidy. And this is what, you know, nobody uses my desk but me, so I don't mind it's a little unorganized, but I'm sharing my code with you and other people. And so I do mind, and you might mind if it's hard to read or it's disorganized. So keep your code tidy. It's just so much easier. And I will have a drinking contest with anybody who tells me it takes more time to write neat code than sloppy code. It doesn't. And then we'll both have drinks. It really is easier just to keep it neat to begin with. And then also document as you go. Now there's a little thing that goes along with these two things. If you choose wise symbolic names for your constants and your variables and your method names, the program becomes a bit self-documenting, and you don't have to have lots of comments on each line. You know, I've put a lot in the stuff that we're playing with today, but most of the time you can write code that is self-commenting, and that will save you a lot of trouble. And then, you know, test and test and test. Listen, you know, we've all released code that didn't quite work as perfectly despite our best efforts, but at least make the effort, especially when you're releasing code to the public. In my programs, and we'll look at this and then we'll go look at that. This is how I set up my Propeller programs, P1 and P2. I have a header. So, you know, everybody knows who's guilty of what they're looking at. I start with timing stuff at the top. Then I define the IO pins, and this is actually two sections. As I was telling you, the P1 I consider has 4 fixed IO pins, and with the P2, it has 8 fixed IO pins. So I put those in a section separate from my application, and you'll see that as we're going along. Then constants, and I may have 1 or more sections of that so I can group them into logical things. Declaring our objects. Now, for those new to the Propeller, an object is an outside file that lets us do other work. So for example, you're going to see at least 2, 3 today, perhaps. The big ones, there's some children under that too, but we have a serial object so we can talk back and forth to the terminal. We have a randomizer object that just simplifies making random numbers so that we can make the lights twinkle and do fun things. And then we have the driver object for the lights. That's an object. So those are those things. We're going to talk about variables more in depth when we look at code, but we define the global variables, any predefined data. This is an interesting thing in the Propeller. You can't define, you know, in a language like C, you can define a variable and its value in one call. You can't do that with the Propeller. You can only define the variable name. You have to define its value separately. But the predefined values kind of let you do that in an interesting way. And we're going to use predefined values for a couple of things today. And then your public and private methods. Well, I'll show you the difference between public and private methods here in just a bit, but this is the structure of my programs. And if we go back to here's that blank program, you can see here's my header. So name, all this stuff. Here is my timing oriented stuff. Like I said, I have decided to standardize on 200 megahertz, but I might change that. These values then give me the clock ticks in a millisecond and a microsecond. Now there's features in the P2 that make these less necessary than in the P1, but I still have them in there. For those of you that have been using my code, I've recently bumped my standard baud rate for the P2 to 230.4 kbaud. Part of that is to match what the standard baud rate is from FlexProp, so it just makes their life a little bit easier. Here are the fixed IO pins for the P2. Now, this set matches this set. There's a bit of shenanigans that go on here. the creation group figured out that they could swap the clock and the chip select pins between the SD card and the flash and make it work. But I define them separately. And then, as I was telling you, we've got 2 LEDs on the eval and the edge that we can use. And we're going to put those to use in a program. Here's my section where I put my pins that I'm using in the application that are specific just to that application. Then some general constants. Here are my objects. Now, I do this just so I can keep track of the number of cogs that I'm running. Because main is my program. So I'm saying, okay, I'm running a spin cog. So I know that I've got at least 1 cog running. I always seem to be using random stuff, so I throw that into my template. It doesn't need a cog though, so that's not marked. But the full duplex serial does use a cog for buffer management. So by doing this, I can look really quickly and know that I'm using 2 cogs in this program. And again, with the P2 and smart pins, we use fewer cogs sometimes. But as John will tell you, and some of my other customers will tell you, sometimes we're watching cog use very carefully and make sure that we don't run out.
And John, for the newcomers here, explain what a cog is briefly.
Oh, I apologize. A cog is a processor, is what we call. So the Propeller has 8 independent processors that are all running simultaneously. We call them cogs.
Thanks.
Yeah. My pre-initialized data is here. Again, we have examples. When our code, you'll see that. Global variables. Now, remember, so again, for some of the new programmers, I should go back up here. A constant, this is what CON is short for constant. A constant is a value that does not change during the run of the program. So for example, this LED can't jump ship and move off of pin 56. It's soldered to it. So it's never going to change. That's a constant. Variables are values that can change. For example, a counter or a random number or something else. So that's a variable. Now, a global variable can be seen anywhere inside this file. So main can, if I define, let's say I define a variable here called Parallax rocks. That variable can be seen anywhere in this code. So this is called a global variable. If I, though, do this, I can define a variable in main. Let's say I want a little thing for my counter. So I usually just shorten that to T for time. This is called a local variable. Now, I have to separate it from the name with this pipe symbol. This is a local variable, and it can only be seen inside main. So for example, not that I would, but just so for, I can show you, if I have T here, this T and this T are different variables. They don't cross paths, they don't see each other. They're in different areas of memory. They happen to have the same name, so that may not be good form, but sometimes for generic things, like many of us use I or IDX for a looping index, or just X, things like that. But local variables only have what we call scope. You'll hear that term in programming books. The scope is just here. Global variables have global scope. This guy can see that, this guy can see that, this guy can see that, etc. So that's variable scope. Now the final thing that's kind of scope oriented is you'll notice that my method names, so those of you again new to the Propeller, we call what C programmers call a function, we call a method. It's the same thing. There are public, that's what PUB is, or private methods. Now, private methods can only be seen inside their own file. So the only place that matters is when they are a child of another. If you look up here in this area of the screen, you can see, well, I've actually compiled a different program, but you can see these are the child objects being used. I don't think any of these has, let me just check really quick. I don't think any of these has a private, well, they don't, but you see all of these methods are private but if or so public rather. But if I made this private, I could no longer use set blue from the next level up because it's only visible inside this object. Now, you might ask why we would do that. Well, for example, I was writing code over the weekend for my friend Casey for this stupidly expensive RGB encoder from SparkFun. It's 20 bucks, crazy expensive. But Casey wanted to play with it, and I thought, all right, let's play with it. It has I2C access because there's a little processor on the back. So I2C is a protocol we're going to deal with later. But my point is, I didn't want the main application to get directly to the I2C stuff. So within the object for this guy, I made the I2C functionality private. So only inside the object for this, those methods could access I2C, but not the top level. So that's what's going on with that. So as again, we use this generic term scope. It's how far or where you can see it. And all right, I think we've covered everything. Oh, finally, a couple of things. And I think I have this on a slide, so we can bull right through that slide when I get there. Within the propeller, the first object that is in the list of, sorry, the first method in the list of methods is what runs. The propeller doesn't care what it's called. Now, just out of habit, I call it main because in the C world, main always runs first. So I do that. Now, I've seen in the forums a couple of times, people that are coming from C to spin think that main runs first and you can put it anywhere. That's not the case. In spin, the first object the first method in the top level object is what runs first. The second thing is, like in C and other languages, when to get to another method, I just call it. Sometimes it will have parameters that we call or arguments will pass along to it, sometimes not. For in this case, setup, this is what I use for instantiating my objects or setting up I/O. So in this case, in full duplex serial, I have a method called tstart, which is for terminal start. And all I have to do is tell it the baud rate. So I made this method tstart, so it already knows what pins to use because they're fixed on the propeller. And I know that it's true mode baud, so I don't have to do any fancy stuff. Within full duplex serial, you have other selections, but for the terminal, we just need those two pins that we always use and this kind of thing. So I just made it very simple. So you can see this, what is happening when I get to this line, it jumps down to here and it runs what's ever inside of setup and then it jumps back. What you don't want to do, what I have seen some newcomers do, is this. They call main thinking that that's what it takes to jump back. That creates a problem. It'll work for a little bit, but then this gets into too much detail. But what'll happen is you'll run out of RAM because of these recursion problems. So when you call a method, once it ends, it will jump back to the next line, if you will, whatever comes next. You don't have to direct it back. Now, there are, when we get into some advanced things, there are ways where we can escape back through a different route or a more direct route, because you can go, you think what's happening, main is calling setup is calling term.tstart. That's actually calling another method inside. So we're getting down several layers of methods. There is a mechanism in the propeller called abort that is occasionally useful if you have a hardware problem and you want to jump right back to the top. You don't want to have to blow through all these other layers. You have to do this though, I think it's what it is, to tell the compiler, hey, if we get an abort, come right back to here. That's advanced stuff. We'll deal with that later. Okay, enough theory. Let's have some fun. Let me make sure I didn't miss any slides. Again, I'm open for questions.
Yeah, John,
Please
there
don't
was one.
Don't
You
be
can
shy.
handle this at the right time. When creating an object, you break it up into small pieces. How do you go about coming up with your naming convention?
Well, let me see if this helps. This is my style things. So when I'm coding, you saw the structure, but then when I'm writing code, this is how I style it. And then we'll look at the internals of my object. Some of it's just what makes sense. You know, you want the names of your methods to be functionally make sense. Now, because of the popularity of the Arduino in the world, I borrowed setup from them because that's what everybody uses. And people understand that's where I'm setting up. So, we have to call it specifically for those coming from the Arduino. They do a thing in the Arduino world, setup comes first and it runs. And then internally the compiler makes it run a thing called loop. We can't do that inside. Now, technically, I guess we could if we did this. So this would kind of run the way the Arduino does, but I don't like it. So I do it my way. I do it the normal way. So let me make sure I get all the way back there. So when you're naming things, main and setup are kind of generic, but here's a perfect example. I do a lot of work through PST, and so when I compile, I have to open up PST and get it ready before I start sending stuff there because I don't want to miss it. Some people will put in an arbitrary delay. I don't like to do that. I just want to know the terminal's open and it's ready. So I made a method called wait for terminal, and it has a parameter here. So if we look down here, and I have some instructions, it says wait for the terminal to be open and a key pressed. So and then I say download to RAM with F10. That's the other thing with the Propeller that's really kind of nice. You can download and run out of RAM, which means the code that's already burned into your Propeller does not get overwritten. So you can do testing without wiping out what's already in your Propeller. You can do it through a RAM test. And I like to do that. It's very fast because you don't have to burn it into the chip. You're just running it right into the RAM. So
and PST, Parallax serial terminal.
Yes. So if I press F10, well, see, I screwed up something here. Oh, I'm on let me go to an actual program. I was on one that wasn't saved. So here, I'm doing the same thing here. So here's my main, I set up, and here's my wait for terminal. So if I was going to run this, and this is our last program, we're going to go into details later. If I press F10, that little thing you might have seen on your screen, I don't know if it went through the stream, was telling me, okay, it's running. Then if I press, oh, sorry, I just did it again, F10. Then if I press F12, PST comes up. Can everybody see my PST?
Yep.
Okay. And now, if you go back to those instructions inside that, it says, enable it. Now, since it wasn't open, it's already enabled, and all I have to do is click here and press enter, and now I have things running. In this case, I'm displaying a menu. So this is just my habit, and it makes it really fast. I was coaching Casey over the weekend a little bit, and he, once he saw that, he's, oh, that makes perfect sense. You write a bit of code, F10, F12, enter, enter, boom, you're running. And it's my habit. What I remember I said earlier in the presentation, have fun, experiment, be willing to play. You'll come up with your own ways of doing it. This is mine, and I find it very useful. Again, this applies to Propeller tool with PST, and the people that are using other terminals may need to find a slight workaround, but it seems to me they should be able to do something similar. It would just have to do a bit of investigating. So again,
can I ask a question here?
Yes, of course.
The thing about Arduino is anytime you use a print statement or open a terminal, it automatically brings up the terminal. Whereas in both Propeller Tool and Prop C, you have to explicitly open the terminal. Is there any reason why we can't just sort of code in a print statement and the terminal automatically comes up?
Well, my experience is different from yours because I always have to click that little thing that says open the terminal, at least the first time. Now, once it's already open, the same thing with PST. If it's already open, PST will disconnect from the serial port if it loses focus, which means you can download again. Because remember, it's the same serial port. So you have only one thing, either the compiler or the terminal can be using that serial port at the same time because they are independent applications. And like I said, I was doing some stuff with I was experimenting with the ESP32 because I want to use the ESP32 as a Wi-Fi bridge for the Propeller. So I was doing programming with it through the Arduino environment, but I found that I had to manually open the terminal. I've not seen automatic open the terminal in the Arduino. That's not to say it isn't there. I've not personally seen it. And once PST is open, it's open.
Okay, thanks.
Like I said, this is my way of doing things. You may, in your case, you may want to just put an arbitrary delay so that when you get to the terminal and re-enable it, and maybe there is a mechanism. There is, because if I press F12 again, see, it brings it back up, but it's in a disabled state. It may not show through the stream, but this button, the enable button, is flashing. So if I click on that, it's now re-enabled and I can access it. And what I like is I don't want to be rushing a timer or something. But Jeff has been really flexible about adding new features, that are useful. And that would be a thing I would suggest that you put out on the Propeller GitHub on the Propeller Tools section. Because maybe there's something I've not thought of or Jeff hasn't thought of, and maybe there is a way to make it a little bit more automatic. Okay. So again, Ken, I hope I answered your question. The naming conventions is make them useful. I try not to get too verbose. My coding is a lot shorter than my talking, but I try to make it, useful. So wait for terminal is pretty specific. Tells you what it's doing. Now, in this case, too, I can pass along an argument that says, hey, I want to clear that screen because if there was any debris in there, get rid of it. I don't have to, though. If that's false, it'll just wait for the terminal to be open and enabled and for me to press any key. Okay. All right. Yeah, styling. Now, this is a thing that is really... It's a sensitive area, and I live and work in Hollywood, and we're crazy about documents. So this is my way of doing it. So if you look at my programs, and a lot of people said I can tell anything that you've written because it has a very specific style. And I didn't create these style rules; these come from other languages and other programmers. I've adapted these for spin in my way. So. I put all keywords in lowercase. For me, it makes the screen less noisy. We always say, like, if you're tweeting or sending text messages, don't put everything in uppercase. We call it shouting. Don't shout in your code. Just use lowercase. That way you're not fiddling around with the shift lock or any of that nonsense. Now, there is a time when we do want to use uppercase, and that's constant values. So if I see something in uppercase in my code, I know that is a constant. If I have a constant that has a two-word thing, I will separate the words with an underscore. Variables, remember, those are values that can change. They're usually in lowercase, but if I have a lot of variables in a program, sometimes I will resort to camel case. I think I told the story about the laser tag code that I wrote that had a bunch of variables that came in from the EEPROM and that were the settings of the tagger, which is the laser weapon. And then you would have to load those into the game element, and those could be changed, you know, or decreased, like your ammo stores. You know, every time you shoot, you're going down. So these variables had the same names, but what I did was I used camel case with a different header, so I knew which were the default variables and which were the game active variables. So most of my code you'll see in lowercase, but occasionally you'll see I use camel case. Now, an exception, and everything is run together. There's no breaks in the things except this exception. If the variable is a pointer to something, and for the new programmers, a pointer is the address of something. And I'll show you that. We're going to use that a little bit later. I use P underscore in front of that variable name so that I know it's holding a pointer. Unlike C, Spin doesn't have specific pointer variables, or pointer types, I should say. And so I just do this as a reminder to myself that, hey, that's got an address in it. So you should be doing address-oriented things with whatever's in that variable. In the DAT section, I tend to use Pascal case, because remember, these are kind of like constants and kind of like variables, because things that are within the DAT section, you can modify on the fly. Oops, I don't like to do that. Okay, there we go. And I will occasionally, and I did this in the laser tag program because we had lots and lots of string output in the program, I will preface it with S underscore that says, hey, that's a string. And strings in Spin are like in C and other languages where it's an array of characters terminated by a 0 or a null, people call that. That's how we define a string. You'll see that in one of the demos we're going to do today. You'll notice, for those of you that have programming experience, Spin looks a little bit like Python, and indenting is really critical to the way it's organized. I use 2 spaces in Spin. I don't like my indenting to get too deep. And one of the best things about the Propeller tool is that each of those sections, remember, and they have colors like, you know, the con, obj, var, dat, pub, pri, etc. Each one of those sections can have its own smart tab stops, and that makes things really nice. So I have smart tab stops defined by section for the way that I like to code things. All right, Spin, you know, I'm going to just blast right through this because I already said some of these things. It is a fairly small language, and you really, if you set your mind to it, can learn to be effective with Spin in a day or two. It is interpreted, and what that means is the Propeller tool will take your source code, which is the stuff we see in the editor, and compile it to what are called byte codes, and that's what gets downloaded into the program. And then the Spin interpreter will read those byte codes and then know what to do with them. So there is an interpretation process, but it's not interpreting your original source. So the original source that we see on the screen inside Propeller tool is not downloaded to the chip. It's a compiled version of that, these byte codes. Now, so it's slower than if you do native compilation. So for example, I've mentioned FlexProp a couple of times. FlexProp it knows how to compile Spin 2, and it compiles it directly to assembly code. So it is faster, to be candid, but you have less code space. So, you know, those are the trades, and we're often making decisions on which is the better way to go. So I tend to find Spin in all the commercial applications I've done has always been plenty fast, and where I needed specific speed things, I can always use assembly. In the P2, that's even easier because it's much faster, and I can use assembly without having to open a cog. That's a neat trick that is built into Spin 2. I just said it a second ago. Spin uses indenting to define blocks, things that are running. I've also said this, you know, you'll notice that Spin borrows elements from Python, C, and Pascal. Like every language, there are a few quirky operators. They're getting less quirky in Spin 2. You know, one of the things that always drove people nutty in spin 1 is that greater than or equals, you know, that operator was equal or greater than in the P1. It's fixed in the P2, so you can say greater than or equals or less than or equals. And the other thing that came, I think, from C, but one of the more experienced programmers will correct me if I'm wrong, the ternary operator is now available in spin 2. I like that that's available. And then I see it's loosely object oriented. Now, I'm not an object orientation expert, but what that means is that our child objects, they have methods in there, and we can call them by saying object.method. So you saw that already with term.tstart. So that's what I'm talking about. Now, what spin doesn't have is what's called inheritance, where if you create an object out of another, the top object doesn't automatically inherit all the attributes of the lower object. You have to make a manual connection there. And we'll see that when we get to the I2C stuff, because I have a core I2C object, and then on top of that, I build other things. So for example, the LCD is 3 layers deep of objects, and we have some manual connections to do all that. I talked about this already. The first method runs, so we've done that. I call my first method main. You'll notice in the documentation, Chip frequently uses go. In my cases, I call setup first thing so I can instantiate everything. And inside an object, if you look, so for example, if we look in the pixel object, if we go all the way up to the top, now you'll see architecturally it's set up very similar. You know, here's my header. I have some documentation information in here. I have a reminder of what pins you cannot attach these things to. Here's some constants. This is an RGB thing, so there's some colors. This is using a child object called gamma. I'll explain to you what that means. We're not going to play with it today, but I'm going to explain it to you so you can play with it between now and the next time. Here are the variables that are global to this object. And look here, my first method is called null, and it doesn't do anything. The reason is if I press F10, I don't download anything, really. I mean, it probably gets downloaded, but it will never run. I can't operate this because nothing happens here. And this is just my habit. I think I liberated this from Ray Roddick, and it just made sense to me, because sometimes you're doing I/O things in an object and you accidentally press F10. You go, oh no, I didn't want to do that. So that's what I do. It's you know, it's not a mandatory thing. Again, it's just my habit. I'm sharing with you my habits. Hopefully the ones that you think are good, you can put to use. Okay, talked about this. Method calls are like subroutine calls. They automatically return. What I should tell you, the P2 is a little bit more like other languages in that you have to declare its return values. In C, for example, and since that's such a dominant language, I'll use a comparison. In C, we tell it what type we're going to return. We might have a void function, which doesn't return anything. We might have, say, a uint8, which returns an unsigned 8-bit value. In the P2, we don't have to declare the type because it's always going to be a long. But we can either return no longs, or we could return one or more longs. And but we have to declare them. So we're telling the compiler, hey, this is returning long special notation. I'll go ahead and show you. If we look in, well, let me do this. I'm gonna compile this and pull up the terminal code. So this is the terminal object. And again, you'll see it looks very much like the other. Again, null at the top. And in this object, this is very long, so I'm gonna go find this right here. This is a method. So you notice it's private. So here, I'm gonna play pop quiz now because my voice is getting tired and I want somebody else to talk for half a second. What, can I call this method from the parent object? Oh, when I ask a question, you answer. That's the
No,
rule.
you
So
Of
if you
cannot.
ask
course
me-
not.
No, you can't do that.
All right, I have to say, Roy, you don't get to answer these questions. You're smarter than all of us put together.
I was waiting for other people, and then you repeated, so I answered.
Okay. All right. Yes. Yeah. As Roy points out, private objects cannot be called from the parent. They can only be called internally. And in this case, what this is doing, get nargs is maybe a little weird name, but it's get numeric arguments from this string. And what is going on here? So you see the colon after the arguments here. That says these are return values. In this case, I'm returning 3 values from this method. And then you'll see, as I showed you before, I also have local variables. So these are going to go back to the caller. These are not. These are just local variables. An interesting thing with the way the propeller works is when you have return variables, they're always preset to 0 going into the call. You don't have to preset them to 0. The compiler does that for you. The local variables, on the other hand, they could have anything in them because they're just pulled from the stack and they're not preset. So they could have been, that's just memory space. It could have been used for something else. So be careful. You cannot make assumptions about what's inside a local variable. You have to take care of that on your own, okay? So if we look here, here's where that's being used. So you see where I have 3 things. This is another nice thing about Spin 2 that comes. I know that Python has it and probably other languages too, but you can see I have 3 variables here, and they're all called, the assignment is coming from here. So does that make sense? This is returning 3 things. So up here, I'm asking for 3 things. So you notice there's 3 there. If I got rid of one of these and went to compile it, it would tell me that there's a problem because this is returning 3 things, but I'm only asking for 2. Now, in some cases, you don't need everything, and I thought I had that in here somewhere. Oh, right here. So let me do some undos to get rid of that. You see this version of that call? In the 3rd space, I have an underscore. That means I don't care about that 3rd reply. So just give me the first 2 things, and I don't care about this one. So that's a neat thing that you can do. I don't use multi-return values very often, but it was quite handy here because I needed to, this is handling the formatting stuff in the string, and I wanted to be able to pass where I am in the string, have a little, this little routine, pull the numbers out of it, and then pass me the address back of where the string continued on. It just was cleaner to do it this way. I felt this is probably something that needs to be readdressed. This fairly early code, but it is working. So that's one of the neat tricks about the Propeller 2 is that you can have no return values or multiple return values. If you have return values, you have to declare them with a colon and then put their names in there. So you'll often see programs that'll just say return and then some value. You still have to declare it here in the P2. So you'll see in a lot of my code, I will have something. I will just do, I will call that return value result. Now in the P1, result was actually the default name of the return value because in the P1, it always returns along whether you do anything with it or not. And, I might do this. Even if you're just doing something like this, you still have to declare that in the P2. Okay. All right. Okay, finally, all looping in the in spin is some construct using repeat. We're going to see that. And conditionals, you know, so you can make decisions. You can use if and else if and else or case. So as far as making decisions and doing things, there's just a few keywords to deal with. So that's why I was saying it's a fairly small language and really easy to use. Finally, there is this really cool thing called the system counter. We can use that for precise timing. We're going to see that later, so I'm going to skip ahead. And as I told you, there are smart pins. We'll use that another time too to do complex tasks. I want to get to the fun stuff today. Oh, final slide, I think, is that in the P1, you had to launch a cog in order to run assembly code. In the P2, you don't. You'll see that in my I2C driver next week or the week after, whenever we get to I2C, because I use 100% assembly code wrapped in spin methods to do I2C. And the reason I do that is so that I can run the I2C clock at a precise rate. I'm also doing my SPI and one wire, which we'll also see. So that kit that Ken put together has a little DS18B20 one wire temperature sensor, and that requires very precise timing. And we're able to do that without launching a cog because we can do assembly inside of method. So we'll get to that later. Okay, finally, let's just have some super easy fun. We're talking about smart pixels. Now, the kit comes with these Christmassy kind of bulbs that have a driver called the WS2811. Now, for those of you that actually have it, or if you've seen the pictures, if you look very carefully, there's a little chip inside the case here. That's a WS2811, and then it connects to an RGB LED. For those of you that might have one of these, these pixel rings or strips, these have the driver and the LED all built together. Now, those are the WS2812, usually 2812B types. The protocol is identical. There's some slight timing variations, but these WS28 whatevers are one wire. So these are what we call asynchronous serial. The other types that are very popular, like the type we used on the Thunder buckle, those are called APA 102Cs, and those use 2 wires. So they're, anything could run an APA 102C because you have a clock and a data line, and the clock controls the timing of everything. So it doesn't care how fast or how slow it is. The WS28 series and similar pixels, though, have very precise timing requirements. Now, they come in 24 and 32-bit type pixels. My driver supports both. The ones we're playing with, the WS2811, uses 24 bits, so that's 3 bytes. So you have 1 byte for red, 1 for green, 1 for blue. But there are other pixels that have red, green, blue, and white. They have a separate white pixel. And you'll notice as you're playing with these, I mean, to make white, what you generally want to do is make red, green, and blue equal, and you'll get white. Well, it kind of works, kind of doesn't work. So some pixel vendors have said, hey, let us fix that by putting in a 4th chip. And that's all very convenient for us because the native data type for the Propeller is called a long, and it has 4 bytes in it. For the WS2811s and WS2812s, we only use 3 of those bytes, but for the, I think they're SK11-32s, they use all 4 bytes. Same driver works with all of them, though. We just have to tell the driver what we're dealing with. The reason this is one of the great things about the Propeller is that the many great things, we can use a cog to get very, very precise timing. So I've never had a lick of trouble with driving any of these pixels. And that's why a lot of professionals in the movie business and elsewhere use my driver code or driver code written by others. It's similar because the Propeller is so good at it. I was at a, I'm not wearing my Hackaday shirt, I'm wearing my Sin Shop shirt, but I was at a Hackaday event and I saw a guy with a project running WS2812s and they were having trouble. And I I kind of smart alecky said, "You're running that on an Arduino, aren't you?" And he said, "Yeah, how do you know?" And I said, "Because you're having trouble with the lights." The timing in some processors is not quite as easy to deal with as it is in the propeller. So the propeller is just a beautiful thing for doing these lighting control things. My drivers, the one we're going to play with today, is called JM-RGBX Pixel. The latest version is in the files that I uploaded today. I have another one for the APA 102Cs. I'm not sure if I've released this one publicly yet, but I will. The APAs are preferred in the movie business because they have a higher PWM frequency, but they do require 2 wires per pixel. So, yeah, you make choices based on circumstances. So because I made kind of a complaint earlier about a lot of people say, "Oh, just make it work, not tell you how to work," I'm gonna put up before I shut up. Here is the data stream for a 3-pixel WS2812. Now you're saying, "Holy cats." There's only one thing I want you to see in this pixel. You notice there are skinny bits and there are thicker bits. The nice thing about this is the data is sent MSB first, so I can read it directly out of this stream. So that's 00000001111. So that's 0F. And then a whole bunch of zeros, etc. Now what I'm going to do is I'm going to put an overlay on that and you can see what's happening. So the first, remember, these are WS2811s, they're 24-bit pixels. And so what's going on is the first byte is my red channel. And then the second byte, which in this case is all zeros, is my green channel, and then my blue channel. So this byte is a dim red, and that's my first element in my color buffer. Here's the green, so you can see that's going on, and then here's the blue. So it's actually quite easy what's going on underneath. The only hard part about this is the timing, but that's taken care of by the propeller. And even the propeller too makes it even easier to do the precision timing. So we can do really, really nice stuff with this. Now, again, some of you are using, what do I do with it? The pixel rings. The WS2812, so if you look at their stream, it looks very similar. You might notice, those of you with eagle eyes, the bits all seem a little bit wider, and they are. But here's an interesting thing about the WS2812s that the driver takes care of, but I want you to know, so if you see it in the driver, you're not confused by what's going on. The WS2812 has the driver and the LEDs built into one element, and for reasons that I don't know why the manufacturer decided, it wants the green element first. So it takes green, then red, then blue. So if I want my red channel first, I have to swap the green and the red bytes. The driver does that. So the storage I'm going to show you inside the propeller goes red, green, blue in order. And but in the driver, we have a condition flag that says, hey, I need to swap the red and the green bytes. And so that happens in the assembly code. Now, for you assembly coders, one of the things that if you haven't seen, you probably enjoy, it made me laugh actually, is that in the P1 to swap these 2 bytes, it took about 9 assembly instructions and a couple of spare variables. And I'm sure somebody more clever than me could make that a little tighter, but I write code to be very obvious so people can learn from it. So it was 9 instructions. In the P2, it takes 1 instruction. There is an instruction in the P2 called move bytes, which will let you shuffle around the bytes inside along in any order you want. It's amazing. So I went from 9 bytes plus 2 variables to 9 instructions and 2 variables to 1 instruction. It did make me giggle a little bit, you know, because I'm a big nerd. And before we get to the coding, for those of you that celebrate Christmas, Merry Christmas. That's me. That's my sister. This was in 1967. I used to be cute. You know, age will do it to us all, but see, I was cute one time. All right. So let's look at code. Questions, because I've covered a lot and we've gone quite a long time. Okay. when I was a younger guy working for Toro, I had the good fortune of getting to learn to drive race cars from the Skip Barber School. And they had a phrase, slow in is fast out. And it was referring to corners, because you don't want to overcook a corner and slide through it. You'd rather go a little more slowly in the corner and be able to come out of it very fast, especially if it's the last corner and this, start finish line is right there and you're in the lead. So we're going to go very, very slow at first, but after a few programs, we'll be right on it. So even if you've never seen this, I hope you feel a little comfortable. And again, even if you don't get to do it today, as soon as you have a P2 in your hands, begin to play. It's really hard to break things with code. With wiring, that's a different story. So let me say, if you're brand new to wiring things, be careful, get guidance. And if you didn't get it for Hanukkah, or you're not going to get it for Christmas or Kwanzaa, buy yourself Getting Started in Electronics by Forrest Mims. Or download all of the Parallax books, even for the basic stamp, because they'll give you lots of good electrical advice. This is a unique thing that we do. We're doing programming, but we're doing programming for circuits. So we have to obey the rules. I said in my last presentation, it's called Ohm's law, not Ohm's suggestion. If you break the law, you might break a component. Now, the interesting thing I will say, although this is not licensed to do silly things, the P2 is really resilient, because I did a direct short between two devices and I thought I killed my P2. And I was crushed because it was a Rev C board. And I thought, and I did it to 3 pins. And I was just crushed. And I mentioned this in one of these calls. And then Chip said, it should have been able to tolerate that. Well, I had kind of put that board off to the side. I picked it up and tried it, and everything worked. So I think it just got very hot, and then it healed, or there was some kind of miracle, because it's working fine now. But still, be very careful with electrical circuits.
And John, just a quick question for you. I sometimes get very confused about directories and structures. And when I download the zip and I unzipped it, it had subfolders, correct?
There should have been 2 folders in there, one called code and the other one called library.
Thanks. Okay.
So the files that are in library, put that into your Propeller, put all those files into your Propeller library. So just copy them over there so that they're available to the compiler. The other files you can put anywhere you like. But I separated them out. Instead of archiving each individual program to where you're going to get a bunch of redundant stuff, I figured out what files you needed and did it that way. I thought that was a better way to go for today.
Thanks.
Mm-hmm. All right. So, in programming, we always have a program typically called Hello World. And so we're going to do that now in the microcontroller world. We can use a terminal and flash LEDs. And since the edge or I told you my desk is a little disorganized. I've already lost my other P2. What did I do with it? Jumping Jim. Oh, there it is, hiding. We have, if you have an eval board, there's some LEDs down there. I only use 56 and 57 because they're not conflicting with the flash or the serial thing. So in this program, now we already had the LEDs named because those are built into the board. So we don't have to name any additional things. Now we've declared full duplex serial, which is our serial IO object. And we should probably, in one of the seminars, talk about serial and how it works, how to take advantage of it, because lots of things use it. For those of you that saw, I think last week, right, Ken? We did the Pixie Cam. That's a serial connection between the Propeller and this device to get color information from the Pixie Cam. So serial is quite useful. And this is an area where the P2 smart pins save a lot of coding for those of us that are writing drivers. And let me say, I understand not everybody is going to write their own drivers, and that's okay. what I want, kind of my mission, is to give you a whole bunch of information so that if you ever decide, hey, if that ding dong JonnyMac can write a driver, I'm going to give it a try. And you'll have the information. I don't want to hide anything. Nothing's obfuscated. It's all right there, so you can do your own thing, because it's a lot of fun. I have many friends that I've made through the community and customers and that, and I guarantee it makes me so happy when one of my friends or customers, which are usually those two elements go together most of the time, they'll call me and say, guess what I made? It makes me very, very happy, because it's an act of creation. And I think that's kind of our human nature, is to create. So enough of that. All right. So here, if you look at my, my template program, this is just using that and adding some blinkies, because I throw that right in. If you call it my template, now you have to save it. Oh, and this is a thing with the P2. So let me just say this about using Propeller tool. With the Propeller tool, you'll notice here, hopefully you can see this. You notice how this says P2 in front of this? So the editor knows that this is a P2 file. You see that this one here says Untitled 14. The editor has no idea what this is, so it's going to assume it's P1. Now, long term, Jeff has, I don't want to say promised, because he might say, I never promised you that, but I think he's indicated that this mark will tell the compiler. So even if you haven't saved a file, it will see that and say, oh, I need to use the P2 compiler on this. And this is not my creation. This comes from the way we did things with the basic stamp, because we had basic stamp 1 and basic stamp 2. And we could differentiate what type the file was by putting a mark like that in it. But until that's implemented in Propeller tool, you need to save a new file first. This one happens to be saved. So all I did was I took the template file, and then I added some blinky stuff in it. Now, let me explain this. Remember, I said that all loops are done with repeat. So here we have one, and this is what we call an infinite loop. You'll notice there's nothing at the end of this that is controlling it. And if you look closely inside, there's nothing that's making it jump out of this loop. You'll see that in one of the other demos. One of the neat things about the P2 versus the P1 is it has low-level pin IO stuff built in. And I noticed this has been causing people some consternation in the forums, because they're translating P1 code to the P2. In the P1, we would use the out and dir registers to manipulate pins. In the P2, don't do that. So let me say that again, don't do that. In the P2, just use the built-in pin manipulators. So this is actually a shortcut for pin high. I could type pin high here, or pin low, but, and I probably should have done that for this first one, so forgive me. Pin high, here's the cool thing. With one keyword, it makes the pin an output in high. It's like, for those of you that go back as far as I do to the basic stamp, remember we had high and low. This is exactly the same thing. So it sets the direction register and it sets the output bit. Wait MS is the same as the basic stamp pause. It waits for this many milliseconds. And what the heck happened? Oh, there we go. And so I'm doing it again. And all I'm doing here is I'm going to do a little wig-wag thing. So for those of you that have a board with LEDs on those two pins, you could run this. And if I do, now what happens is, remember, it's sticking here because it's saying, hey, I want you to open up the terminal so I can say something. So if I press F10, F12, and enter, then I get hello world. And I don't know if you'll be able to see this without me tearing all my wires apart, but right here, can you see? Probably hard to see, but my two LEDs are going back and forth on my edge. Okay, so you're a programmer now. If you've never done this before, you've done the basics. And here's the thing. Everything starts here and just goes up a little bit at a time. And that's what's important, is that, you know, the people will often say, how do you eat an elephant? One bite at a time. And if you're a programmer, you spell bite, B-Y-T-E. Do things incrementally and little small things. So let's say, for example, we wanted to make this a little fancier. So we can go to this second version and look to see what's happening in here. And so that we don't have to wait, I'm going to comment out these instructions. And so this is something I should talk about if you're new to programming. If I put an apostrophe at the beginning of a line, you notice how it changed colors? I have removed that, not from the source listing, but from being compiled. The compiler will ignore it. We call this commenting out.
And John, I have a question too. I'm wondering if anybody who's watching wants to see the process of opening Parallax Serial Terminal.
Oh, did I not do? Oh, I can.
You
do that.
did,
Yeah.
but sometimes this is just a little bit of a sticky point.
Oh, all
And
right.
I
sure.
bounce around, and it's because the baud rate isn't right, or because
Oh, yeah. You know what? Okay. Yes, you're right.
just
So
show
let
it
me
real
do that.
fast.
So we'll do that.
There's
So
someone out
we'll
there
leave
as dumb
this
as
as
me.
is. So now remember, I'm sharing with you my habits. You could go up here and you could say run, compile, current load RAM, or you can just press the F10 button. So I do this key thing. I'm doing F10, F12, enter, enter. So I've pressed F10. Now if I press F12, that will open Parallax Serial Terminal. Now, here's an interesting thing. You notice how it's already enabled. If it says disable there, that means it's already enabled. The reason is it's a fresh open. And so now what Ken was talking about is when it first opens, it may not know what port you want. So you have to select your COM port here and then the baud rate. Now, like I said, for my demos and for my code going forward, I'm going to use 230.4 kbaud. Now, the way that you can find your I'm going to go ahead and close this again. If I press the F7 key, then F7 it doesn't identify, and it tells me that it found a propeller on COM9. So if you don't know what your device is, and especially if it's a new device, like let's say you got a brand new JonnyMac kit and you get one of those shiny new prop plugs with the micro USB, it's probably new to your system. So plug it all in and then press F7 and it will tell you what its COM port is. Then when you press F10 to compile, F12 to open PST, now you can set your COM port here. Now, of course, I've been programming today, so it already knows. And then you'll set your baud rate because it doesn't default to 230/400. It defaults something else. So set it to 230/400. And then if this button says enable, it is flashing. You want to click it so that it's stable. And then in this case, nothing's happening on screen because I'm sitting here in wait for terminal. It's wanting me to press a button key. So I do that and then hello world shows up. It sounds like a lot, but after you've done it a couple of times, it just becomes habit. It's F10, F12, enter, enter. Because when you go into PST, so I'll show you if I do it again, if I do this, if I say propeller, so if I change this, and then I say F10, F12, you see now it's not enabled, so I can press enter because that button has focus. And now it moves the cursor. You notice it's up in the entry line, and I press enter again, and now it does that. So once you get into that habit, if you're using Propeller tool and PST like me, secondary compiles become F10, F12, enter, enter. And it's on your timing, so it's when you're ready for it. That makes sense?
Yeah, that's just saves a lot of keystrokes from what I was doing, to be honest.
Like I said, it's a habit thing. You'll notice, one of the things I'm trying to learn is 3D modeling. And the 3D modeling guys will say, learn keyboard shortcuts. I like to have toolbars and things like that, but if there is a keyboard shortcut, I'll put it to use. And this is a case you can do here. So just remember F10, F12, enter, enter. If PST was already open. It's only enter once if it wasn't open.
That was one of the nice things of the Propeller IDE. It did that automatically.
Okay.
The Propeller IDE can switch back automatically. You didn't have to do that.
All right. Well, we should ask Jeff. You know, he knows, you know, I mean, you can see he's in, even though Propeller tool is a separate application, through Windows messaging, and, you know, I know Roy snickering at me, say, McPhailin, you don't know anything about programming Windows, but there's some kind of messaging structure, I think, inside of Windows, if I'm not mistaken. So perhaps there is a mechanism for doing that and just letting it fly.
There are multiple mechanisms for doing that under Windows, yes.
Oh, cool. One of the things that I would, you know, I was talking to Jeff about is I hope that Propeller tool does get some improvements, because I noticed, especially with the guys that are using FlexProp, and they're using, you know, different terminals that have ANSI escape codes built in, so you can do color strings and things like that. That would be kind of nice too, because I do like fanciful debug output, you know, in a terminal. And you'll see that. I have a menu thing that I often do. Okay, so here we're going to look at, this is the program just with a slight modification. So I have my major repeat loop. And then I'm turning off this LED. This is an interesting thing about the P2 LEDs that are on the boards. They're active low, so making them high turns them off. So I'm turning off LED number 2. And then here's another variation of repeat. I am repeating what is within this loop exactly 3 times. And so this is, I like this. It's a very elegant, simple approach. You just say repeat 3, boom, that's it. Now this can be a variable too. I'm using a constant, but it could be a variable, which is useful in other cases. And this is doing the same thing, where now in this case, I'm flashing on and off the LED 1, and then I'm swapping over and I'm turning off LED 1 and I'm flashing 3 times LED 2. So I'm getting kind of like a policing where I'm going bump, where's my hand? I'm going, you know, bump, 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 but doing it very fast. And again, you know, if you play with that, you know, you turn it on and you see that. And this is one of those things, yeah, we're just blinking LEDs, but when you, especially when you're new, if you do this deliberately and you see the code and then you see the output, it starts to sink in. And this is why I was saying earlier, be willing to experiment and play. Give yourself a little bit of permission to play. And you'll find, and I should say this, I generally preface any time I give a talk like this, my mentor was a guy whose picture is over there, a guy named Cliff Osmond, who trained a lot of actors, some very famous, some like me, not so famous. But one of the things Cliff used to say, because he understood human nature so well, is that humans often give advice that they need to hear. And so I'm saying that everything in this presentation is a reminder to myself, and I hope the things that I'm reminding myself are helpful to you. And so give yourself permission to play, and be creative and do it. Now, I think a bit of advice that I gave, and this is where the forums are useful, because there's lots of people in the forums that need help, that might be stuck. Give them a hand, because it gives you the opportunity to learn something that you're not stressing about because it's not your project. And you learn, and then they get an answer and they learn. So everybody, it's a benefit to the community. It's why, you know, many of us that are on this call, we're in the forums fairly actively and always sharing information with each other, helping each other out. It's a nice thing. It's a fun part of being a part of the programming world. Okay, last version of Hello. Why is there a last version? Oh, here we go. One of the things that happens, you know, notice I have this number in here. Now, I'm using a named constant for the LED, but not for the time. Although in this case, I'm using the same time throughout, 50 milliseconds. Well, if I wanted to change this to see how it looked, I got to make 4 changes. And now somebody might say, well, just do a global change. Well, that will change every 50 in my program, and that could create a problem. So I don't want to do that. What's useful then is to change it one last time and just define it as a named constant. And so this program will run like the last program, but now the timing is controlled right here. So this is the value of using constants, is that you can make adjustments to your program and tweaks that you don't have to go through line by line and make edits. Now, I've had friendly debates with my friends in the forums, because some people will say, oh, geez, we don't want to inundate users, beginners with all of this crazy information. Excuse me. But I think it's not hard, and I'd rather say do it right the first time than develop a bad habit. Now, you know, there's a phrase that gets thrown around by programmers called magic numbers. I don't consider a value inside wait ms a magic number, because we know that it specifically means a number of milliseconds. So there's not magic. It's a specific thing. But there are times where in this context, if I'm using the same value over and over again that might change, it's better to just name it and then change it in one location.
100% agree.
Okay. All right. Okay, let's light some LEDs, shall we? So this ramps things up a little bit. Now, for the old timers, this is easy code, but new people, don't stress. Give it a run and then start to play. Excuse me. Again, I started with my template, but in this case, we have an output to the pile of LEDs.
And this is program 04RGBX pixel
Yes.
demo.
Oh, sorry. Yes, I should
That's
have
right.
called it
It's
out.
hard.
Thank
The
you.
tabs don't magnify.
Oh, okay.
That was a feature I wanted to ask Jeff. I forgot to ask him yesterday. It was, can we get adjusting the font size of the tool? Because on my 4K monitor, the
Yeah.
menus and everything are super tiny.
Yeah, let's ask them for sure.
Yeah, that would be, if anything, that should be the first thing he should fix.
Okay, we can get that done, I believe.
Yeah, you know, Jeff, I found, has been really responsive. He's got a big pile of things to do, but you know, the Propeller tool is useful. Now, long term, once we get it all, you know, really nice, I'm hoping, now I don't know how to do it, I wish I did, but I'm hoping we can take Propeller tool and make it cross-platform and have it work as well as it works in Windows, on Mac, and on Linux. I think that would be really good. And then everybody is doing the same thing. And, you know, of course, that means other people are using other tools, and that's great. But I really like Propeller tool. Luckily, I'm primarily a Windows user, so, you know, I'm okay.
I've been asking for that for a long time.
Yeah, I wish it wasn't in Delphi, because I could help Jeff get these features in and get it be cross-platform if it was in a standard language.
Well, I think there's more to it than that. From what Chip said, there's some third-party.
Yeah, but we could write our own if it wasn't, if the whole rest of it wasn't in Delphi.
Well, isn't Free Pascal pretty much Delphi compatible now?
But that's not the issue. I don't know Object Pascal well enough to write stuff in it.
It would probably be better. See, you know, it's funny because people think I'm anti-C. I'm not. I just don't tend to use C on microcontrollers very frequently. You know, in fact, you can ask Chip. He'll tell you how many times I've called him and harangued him about, you know, telling him to stop writing the compiler in x86 assembly and write it in C so that it can cross-compile to other operating systems.
John, do we have to select 04, that program as the top object file?
No, yeah, it's what Ken is talking about there in the Propeller tool. This is a feature I never use. There is a feature called the top object file. The reason for that is it lets you compile it no matter what tab is open. If I've got this tab open, this is what's going to compile and download. So that's where the top object file is. You can compile the top object file no matter what tab is open. Again, to me, it's kind of a blindside thing, so I don't use that.
Thanks, John.
If you do set, for those since you brought up Ken, if you do set it to the top object file, you'll notice that the font will be darkened or bolded. So you know that that's the top object. Okay, so with Pixels, we now have another device that we're talking to. And as I was talking earlier, the WS2811s that we're using in the Christmas light string, and or if you're using one of these, the rings or strips, you know, from Adafruit or other companies, it's a single wire device. So here is that wire here.
Hey, John, I got
so
a quick question.
Yes, sir.
My lights did not come with any instructions as usual.
Oh, thank you for bringing that up, you know, because I assumed everybody knows what's going on. So I have a nifty way of doing this. I will, after we're finished tonight, if that's okay with you, I will put together a nice drawing and post it. I don't know if I can lift this up, if it'll, because I have a green screen, I don't know if it'll show up, but what I'm using are, you know, if you get these wires, Parallax sells them, or you can get them all over the place, but you can get them from Parallax, and you can get female, female, male, female, and male, male. The male, female, and the female, female are the most useful. So what I've done is when you get these wires, let me turn off my thing so I don't break something. It has a little black connector. Now, one end of the system has a label on it. That's the input side. It also, the little black connector on the wires has female sockets. That's the incoming end where the female sockets are. And so what I've done is, it may be tricky to see, is that I've taken 3 male-female wires and I plugged the male end to the corresponding color. So I'm following their color scheme. I'm using blue for ground, white for signal, and red for 5 volts. And I plug them in. So these are male pins going into this female socket, okay? These are male, these are female. This is female. Then I'm using the female sockets on the other end of those to go into the male headers on the JonnyMac. Now, the other thing that you do need to be a little careful with is that these strings that are coming in the kit, they have pigtails with stripped ends on both sides. Do you see those? Hello?
Yeah.
Yep.
Yeah, I see them on
Okay.
mine.
I'm not seeing anything there.
Well, I'm not saying not on mine, but on
If you have the kit.
If you have the kit, the first pixel has 3 wires coming out of it, blue, white, and red, that go to a black plug. It then has an additional red and an additional blue wire that come out and just have a stripped and tinned end. At the levels that we're running, you don't need these other wires, but you do need to protect them because that's your voltage. So put some painter tape, or I used heat shrink on the end that I'm not using. So on the opposite end, oh good, Ken's gonna show this up close.
Yeah, let's see here. Just have to make sure this camera's working right. 1 minute.
So what I did on my strip is that I took a red and a blue female wire, and I removed the plastic shell from one end. Then I stripped and tinned the pigtail that was on the LEDs a little longer so that it was stiff, and I plugged it into the socket. And then I soldered that whole thing, and then I covered it with heat shrink. So now I have 2 reds and 2 blues so I can carry more current into the cable. Then on the outgoing end, since I'm not connecting anything else, I just put heat shrink over the ends to protect them so that they don't short against anything.
And there's not enough voltage on the JonnyMac board to run this, correct?
Well, remember, you're running this from 5 volts. So the power supply that comes with the JonnyMac kit is good for 3 amps. So you can run these at very low levels, and these are inside. So if you look in Ken's, the one in Ken's left hand where that's female, that's the ingoing side. So take male, female, put the male end into there, and connect the female end to male pins on the JonnyMac.
And the white wire is the signal wire, right?
Yes, and that's going to go to pin 48 in my code. You can use whatever pin you want, but I'm using pin 48. So I already see a problem in Ken's setup. You see where his thumb is? You've got a loose blue wire with those wires are live when you have 5 volts. So put tape over those things. That's what I was trying to prevent, because God knows they'll find a way into hitting some metal. So yeah, we want to protect it. And the reason for that, if you're running these things really intensely, you can have some voltage losses through the cable. So I've done this. I did a children's museum project in Knoxville, Tennessee, and we had about 45 feet of LEDs. So we put power supplies on both ends. And that way we didn't have any brightness drops through the cable.
Yeah, so as long as your 5-volt input to the JonnyMac board is got enough amps to run the LEDs,
Yes.
you can run it from the 5-volt connections on the board.
Yes,
and I've tested
thank you,
it.
Roy.
I've tested it with what comes from Parallax, and it all works. The LEDs all.
If you're
light.
running dim, if you decide you want to go crazy, I put a link in this project thing in the forums to a heavier power supply.
I've got a 10 amp 30 volt bench supply that'll do it.
As long as you're putting 5 volts into the board, you're fine.
Now on the one wire signal, the voltage there can be 3 volts, right? On those other two?
Yes, as long as it's not a big long distance between the propeller and the device. The spec looks like 3.3 volts shouldn't work, but it does. Now I will tell you, I had tried it through on the middle of the JonnyMac. You can see in Ken's board, you see those big capacitors on the board, and there's 4 servo headers adjacent to that. The signal wire that is connected is associated with, it's a little hard to see, there's a socket right there by the breadboard. There's a female socket, and between the white male header that's marked up, was marked signal, and that female socket is a 1K resistor, and that will interfere with this signal. I tried it yesterday and it won't. So just take the signal directly out of whatever pin you want to use. Again, in my code, it says 48. You can use whatever you like, it doesn't matter. But go directly from the P2 into the white wire, and then connect your power and voltage to 5 volts. Remember, it's 5 volts, not 3.3, and ground, and you'll be fine.
And on the JonnyMac, that pin 48 has 2 ground sockets to the right of it.
Yes.
It's just hard to tell.
The other thing too, this Casey and I ran into this when you're using the JonnyMac on near the left side of the breadboard, or near the P2 side, there are jumpers that enable the 5 volts down each side. So you got to move those to have the 5 volts on.
Yeah, I learned that the hard way, didn't we?
Me too.
That's this jumper right here, John, right?
And there's one on the other side too.
Yeah, what I didn't realize is that there were 2 of them. So when we went and did it, I could, because I was using it on the other side of the board, and I couldn't figure out why nothing was coming on. And John goes,
too.
"Hey, guess what? There's another one up there." So I went and flipped it, and everything came on, and it worked great. But
I'm not seeing the other one.
It's right there. It's right in the middle of your screen.
I'm looking at it. Okay.
Yeah, there's one on the top and one on the bottom, and then you can turn them on, or you have to turn them off and on separately. So doing one doesn't give you everything. You have to do both if you're going to use a power supply in both places.
Yeah. Yeah, Michael did a really nice job on the layout and design of this. A lot of people, just for the record, because people have been overly kind in giving me too much credit. I did a very simple sketch in Dip Trace saying to Parallax, "Hey, I want something like this." Well, it turns out that guys like Roy and even Chip and a few others said, "Yeah, I want that too." And then Ken, being the big boss that he is, said, "Hey, make this happen." And a couple of weeks later, we had this really nice board. So thank you, Ken and Parallax, because it's a really nice development board, and I'm excited to be doing P2 stuff with it. You saw that picture earlier, and Casey, who was just speaking, he's one of my friends / family members. We were playing over the weekend with I2C stuff, and it was really fun. He was able to plug in I2C components in the board and experience the joys of I2C for the first time. We had a great time.
Ken,
Hi. Hi, Carol.
hi. Do you remember the article I did on how to drive linear actuators using a flip?
I do. With
Yeah.
Buckley.
Wouldn't that little conversion circuit I made on the breadboard the flip was on, wouldn't that work for a lot of, I know you don't need it on this board because this is a development board with many things, but if somebody's wanting to do this same kind of thing with a smaller board, a smaller propeller, wouldn't that be just as easy? Because it was simple, it was quick, very few components on the
You'd have to
breadboard.
bring that up and show it.
Okay, I can do that. It was, well, I don't have it. I'd have to.
It was a
dig it
level
out and remake
converter,
it.
right?
Huh?
It was a level shifter that you made.
Yeah, it was just a little converter.
Yeah.
The linear actuators can only take 5 volts.
Oh,
That's
And the
it.
flip
Okay.
can only put out 3.3 volts. So it was
3.3.
just a little
Yeah.
converter that turned the 3.3 volt signal into a 5 volt signal, and everything worked great.
yeah. There's a bunch of things. One of my favorite devices, Carol, for that is the TC4427, because it's actually designed as a power MOSFET driver. So it'll take, you know, and you can decide what your input and output voltages are, because it will go up to 18 volts on the output. But I use it all the time as a 3.3 to 5 volt because it has a totem pole FET output. So it's really stiff. One of the projects that I did with my friend Lou, who used to have camera turret, is we were controlling camera lens using standard servos. And on the bench, everything worked great. But then when his customer added a 30-foot cable, it became a problem. So what we did is we put a TC4427 in there. So it's just one chip. And then we actually ran it at 6 volts. So we had a little bit more signal going out to the servo. And his customer was thrilled because he was able to run these servo pulses through a very long cable that wasn't anything fancy. So that's, I'd like to see what circuit you're using, but that's one of my favorites for anybody that is wondering. In fact, on that little board that we had remember I showed you the picture of the Prop Mini that was on that little hand etched board? Underneath that Prop Mini was a TC4427, which was shifting the clock and data line to the APA 102Cs from 3.3 to 5 volts.
Yeah, that whole thing is in Robot Magazine. It was back when I was still writing for Robot.
Okay. But these little cookbook things are things we need to share with the community.
Definitely.
Because, you know, here we're going to be interfacing 5 volt devices from time to time.
John,
my gist is I like to try on the projects I do for Parallax to use all Parallax products. So for me, it was easier just to use the little components on a breadboard. That way it was all stuff you could get from Ken. It's just a thing I have.
Okay, no, I get it.
Well, she runs Parallax Museum Northwest. John, my LEDs are getting enthusiastic.
Let's light them up, dude. All right, so to our program, let me get to, well, Ken took my.
Yeah, here, give it back to you. There you go.
Let me get to, where's my, editor. Okay, so here. All right.
My power supply says in Christmas mode, I'm using 0.049 amps.
0.049, okay, well, 50 milliamps, so you're not hurting anything.
Yep.
I couldn't wait till mine are blinking already.
Mine are not blinking.
Well, you know,
I went to
there
the later
Mine
program.
So I'm not the only
folks that are skipping ahead. Well, let me explain this stuff because some of the newer folks, we want them to be able to
got to be the driver
and what they're doing. Okay, so let's go through. So we're just
show
for
your screen again.
I need to do
Yeah,
this.
so we could see what you're doing.
Oh, sorry, I was just motoring along thinking.
Is it the fact that your driver supports all different versions of these and we're using the wrong one, John?
No.
Okay.
No, oh, listen here. What I was going to do, and I will do it now, I'm going to hang these around my neck so you can you should be able to see something light up.
Yeah, Ken, the reason yours aren't blinking is that you're not running the later program that has them do twinkling
Yes,
and blinking.
the first programs are static. Yeah, we're building things. Remember, slow in is fast out. Okay, can you see my screen now?
Yes.
And
Okay,
which
good.
program number are you using?
We're gonna start at the easy stuff first. We're gonna start on program 4, which is demo. And I'm going again, step by step, the things we've added. Since we're talking to the pixels, now these are 1-wire pixels, so they need a pin. Now, this is a little advanced, but I'm telling you this so that you can go look at it later. For the newcomers, this chain that I have around my neck has 50 pixels in it. So I've got a constant called n pixels for the number of pixels. It's 50. These are 24-bit pixels. Now I have to know that. And if you bought pixels, the vendor would tell you that. The WS2812 and the WS2811 like these tend to be. There are 32-bit pixels, but those are, I think, WS or SK something or others. At any rate, again, the vendor will tell you. So we're defining our smart pixel driver. We're calling it strip. I took from, an old Arduino program, and just everybody was used to that. So I used it as well. This is my driver. Now, this is a bit of trickery, but it makes better sense once you have more programming experience. The driver for the pixels does not hold the data for the pixels. The reason for that is I might have a 50 unit string, or I might have I keep losing that ring, or a 24 unit device. So if I want to work with both of these, I have to put in a 50 pixel buffer inside my driver. Well, then what happens if I don't have a picture of it, but I did an art installation over in a very expensive neighborhood in Los Angeles that had it. If you could see it, it looks like a giant contact lens. It's about 4 feet in diameter, just stuck on a wall. And inside there are concentric rings of WS2812s, and it does this really slow color wash. So those of you who've seen my driver, you'll see a method in there called morph, which lets you control a phase change between 2 independent colors. That came out of that project. It turned out to be beautiful. I learned a lot about this stuff in between. But again, that was 350 pixels. So getting now to the point, my newer drivers, unless you find something very, very old, and none of my P2 stuff does this, the storage for the colors that we're going to be sending out to these things is in the top level application. And so I have a long array called pixbuff. This is my pixel buffer. And this is where the constants help, because if, I've got it set to 50. I think Dave, said, hey, I've got one of these rings. Can I use that? Sure. And so in fact, I was playing with this ring earlier. I just set my n pixels constant to 24. And now I had the correct buffer size with this. So you can see the value of using named constants because they propagate all the way through. Now I'm going to skip this for just a second and go down to our setup method. Remember, we call setup first, and here's how we start the driver. Now, because there are a number of these pixels, my pixel driver has a method that will start anything, but then I created a bunch of named methods like this that have the details buried in that, like the specific timing for the high and low signals for these guys. Users, we don't care about that. All we need to tell the driver is what we're using. So in this case, it's 2812. And if I wanted to change to this guy, all I have to do is change this to 12B. And now it will use the different values. So these Christmas lights are 2811s. Sorry, I said 12s earlier, 2811s. So this is telling the driver where my colors are. I used the term pointer earlier. So again, for the new programmers, that's the address of something. In Spin, we can get the address of a variable by using the @ symbol in front of it. So this isn't the value of pixbuff, which is actually an array of things. This is where it is, its address in the hub memory. So now the driver knows how to go grab the colors out of it. Here's the number of pixels. This is the pin that I'm going to use. And then this is a reset time. Let me go back really quickly to my presentation. Here was that stream of data. You notice how in the beginning and over here at the end, it's quiet. That's important to the way these pixels work. Because when we have this quiet period, all of the pixels reset themselves and they say, okay, I'm ready for new data. And then what happens, let me go here, it'll be easier to see. Then the driver sends out the first 3 bytes, which are for the first pixel. Those 3 bytes get, since the pixel is in reset or has been reset, those 3 bytes get routed into the internal LED PWM engine and create the color. Now, when those 3 bytes come in, the pixel switches its input to its output. So instead of going to its own LEDs, whatever's coming through the input goes to its output. So now these next 3 bytes are routed to the second pixel. So this is a really kind of clever scheme. And what it does is it makes everything self-addressing. So the first pixel in the stream is going to get the first 3 bytes. The second pixel in the stream is going to get the second 3 bytes. Now, the one downside of this is if you get a break between pixels, you lose everything downstream. And in fact, remember that I showed you that video with the surfboarders, the snowboarders that had the big LED suits on them? Rick said that was a nightmare. You know, those guys are out in snow and cold and they're breaking, so they had to do a lot of work to keep those things running. There is another newish type of pixel that is included in my driver, although to be honest with you, I don't have any to test with, called a WS2813 that has a bypass mechanism. And the claim from the vendor is you can lose 1 pixel and not lose everything else downstream. We'll have to try it. All right, so this now, in case anybody's wondering how that data gets to each individual pixels, here's how it is. First pixel takes 3 bytes and then it switches its input to its output. Next pixel gets 3 bytes, then switches its input to its output. And that happens all the way along. And that switch from input to output stays active until the line goes quiet for a while. And then all of the pixels reset themselves and then we start all over. So that reset period is very important. One of the things you'll find if you experiment with pixels is if you have a lot of them, the reset period needs to be longer than the specification suggests. Otherwise, you can get, now this is getting a little advanced, you get reflections in the line and it creates these little sparkle effects that until we figured out what was going on at that art installation, we thought the house Wi-Fi was messing with us. Because it seemed like every time somebody was accessing Wi-Fi, we were getting this weird sparkle effect. It turned out not to be related. Once we extended the rest period, then everything was fine. That's why in the driver, you have the ability to control the rest period. Okay, so once we start it up, what this program does is presents a menu. So here is a menu, and this is just a big long chain of characters that ends in a 0. This is a string. And so we can use a string method to send it to some kind of display device. This number 13 is a carriage return. Now this, for you people that are, for those of you that are not using PST, PST does a little under the hood shenanigans where if it gets a carriage return, it actually adds a line feed to that. So technically this is a 13 and a 10. You might have a terminal that doesn't do that. So if you're using this, you might need to manually add a 10 to these lines. So you get the carriage return and then you go down a line. And so when this program starts, we're doing the same thing. We wait for the terminal, and then this method .str will print a string on the terminal. And remember I said earlier, strings you have to pass as a pointer. So this is saying, hey, pass this, the address of that, and it will now print it out. So if I do this very quickly, if I do F10, I turned off my board. If I do F10, F12, enter, enter, now you can see here their size is different, but this menu is now printed on PST. Everybody see that? I'm going to assume yes.
Yep.
Now,
John?
Yeah.
I have this set up with a camera and terminal and the code. Should I show it
good.
briefly?
Yeah.
Okay.
Yeah, if it's easier for people to see, absolutely.
Because I don't know who has hardware and who doesn't, but do you see that?
Oh, yeah, there we go.
Okay,
Yeah,
so
much better.
I'll enable PST and we'll just run through this. There's red, white, green, Christmas, random.
Yeah, so what Christmas does is just goes red, white, green, red, white, green, red, white, green. Christmas random randomizes them. And these are all static displays in this first one.
I'm going to have to make it into something because just laying them in a mess like that drives my OCD.
Oh, sorry.
up the wall.
So Ken, if you hold down question mark, it will blink.
Okay, cool. We'll try that.
Oh, yeah, you're forcing it, aren't you? There you go. There is a version in a later program that does continuously blink.
Okay, back at you, John.
Okay, so if we do
Turn your sharing back on.
Yep. If we look at how Ken was able to do that, once we've printed the menu here, then we go into the main repeat loop. And now we're getting a character from the terminal. Term RX will wait for us to press a key, and then it will send it back to the user. And so I'm using K for key as my variable. So here I defined a local variable K because I don't need this anywhere else. I only need it here. And here where I'm getting K, I'm getting the key. Now, once I have a key, because this will wait until I actually press something. Once I have a key, I can look to see, hey, is it a lowercase r or is it an uppercase R? Because if I say to you, well, press R, to humans, lowercase and uppercase R is irrelevant. It's an R. So remember, controllers and computers are very specific. You have to spell it out for them. And so we're looking for both. This double pipe symbol is a logical OR. So this is saying, hey, if the user pressed a lowercase r or the user pressed an uppercase or, run this code, which is calling a method inside the strip, which is the LED object, and it's setting all channels to dim red. So you're saying, okay, great, what's dim red? Well, that's defined up here. Remember I said we could predefine values. See, these are like constants, and we could have used a constant to do that. But I tend to do these kinds of things inside a DAT table so I can manipulate them manually. So if you look across the top, I've put RR, GG, BB, XX. Remember what I told you, the Propeller uses a long as its data type, its base data type. And so we have 3 possible colors, red, green, and blue. So the upper byte is the red color level. This byte is the green color level. This is the blue color level. And this is irrelevant in these pixels, but in other pixels, it could be the white level. But all of the colors are lined up that way so that this color combination will work with either type of pixel. If you look into the pixel driver, here is a code. Now these are full brightness, so be careful using these on your string without an adequate power supply, because you can see here red is FF, so that's full 255 max brightness. You can light up a couple of LEDs that way, but I wouldn't go too much farther unless you know your power supply can handle it. Same thing for green and blue. Now I was just doing Christmas colors, but you can see over here that you can, through a combination of mixing, and you know, I've gotten these from a bunch of places. From this guy, Lachlan gave me some input on things. I made some inputs, and I've structured them, because you'll notice that here white 2, again, for the 32 channel pixels, they have a white chip. So you can use white and get a pure white, or use this white to brighten up the rest of the colors. So now you know, now remember, this is, I'm trying to relate this back to the data stream you saw. Here is the, in this pixel, we're only sending 24 bits. So when we were sending red, you remember we had 000111. Well, that's 0F in hex, and then the zeros. So these are the 3 bytes. Now again, for 24-bit pixels, we don't ever transmit that. So now part of your, for those of you that are new and want to play and experiment, yeah, I only created 3 colors here. You should create a whole bunch more. Now, Ken showed you the red and the green, you know, so those are just solid colors. We're doing the same thing. Now, if we select C for Christmas, this runs a method inside this called Christmas colors. And what this is going to do, here's another version of repeat, where I'm going from a starting value to an ending value. And so I'm going from 0, because arrays inside the Propeller, like every other programming thing you've dealt with, are 0 indexed. So if I have 50 bulbs, their index is 0 to 49. And so I can spell that out here by saying my channel is going from channel 0 to whatever number of pixels I have minus 1. That's going to be my last one in a 0 index string. And now this is a little bit tricky, so let me explain what I'm doing. Up here, I have 3 colors: red, white, and green. The way the Propeller works, it will treat any section of memory as an array, even if we don't explicitly declare it as an array. But I like to make things a little easier to understand. So what I've done is, you notice how I've put colors here and I put long but nothing after it? This is a trick to tell the compiler, I want this and this to be at the same place in memory. And what that allows me to do then is create colors, treat colors as if it's an array, because technically it is. It's these 3 things. And so their index is going to be, this is colors 0, colors 1, colors 2. And in this method, what I'm doing is I'm starting with IDX is my index into the colors array. So I'm going to pre-initialize that to 0. And then I'm going to loop through all of my pixels. And then for each one, I'm going to use the set command for the channel. And I'm going to grab the whatever from my colors array at the current index. Well, remember, I want this to display red, white, green, red, white, green. So what I do is I increment the index. So plus plus index will add 1 to the index. And I say, if my index hits 3, I've now run past the end of my array, so I run back to 0. So this has the effect of going 0, 1, 2, 0, 1, 2, 0, 1, 2, 0, 1, 2 for as long as the string is. And what this gives me, if I run this, is I have red, I don't know, red, white, green, and I have that all the way through the string. So that's the Christmas display. Now, random is if we press a question mark. And what this does is it uses, it just loops through all of the pixels, and it uses a method from my random thing called xRandomize, which uses the internal, it's called a Zoroshiro, I think, randomizer, which is really random. And in my xRandomize method, you can set the low value and high value. These are inclusive. So it will give you a random value between those two things. So if I go back to the menu and I press question mark, I'll now get red, white, and green, but they'll be random. They're not in any particular order. Okay. Now, that's all well and good, but you know, none of us like static lights. We like things to move. So if we go to program 5 and run it, then if we run Christmas, you'll notice that it's moving. Now, the way that we did that was we updated the Christmas method. So here's the Christmas method. You notice it's a little bit longer. And it is inside a loop because we want it to keep running until we tell it to stop. So you'll see that it works pretty much the same way to here. This, we start with an offset that allows us to move the animation. So that's an added variable. And so our index starts with that. Here's where we run through and we set the three colors in their order, starting with whatever this color is. We're gonna wait for 1/4 of a second, and then we're gonna bump the starting colors. This offset, I probably could have given this a better name. This should be called starting color, because that's really what it is. It's the starting color that we're doing. So it starts out initially as red, then on the next cycle through, pixel 0 is going to be white. And then on the cycle after that, pixel 0 is going to be green. And so what we end up getting is this movement of colors. Now, at some point, we probably want to stop this. So we have the ability to look to see if the user pressed a key. That's what I'm doing here. So RX check is a method that is inside full duplex. It will say, yes, there's a key there. Here it is. If there's no key that has been pressed, we'll get back -1. But in my case, I want to look for a specific key so I can't accidentally run out. So I've created a constant in this program called ESC, which is 27. That happens to be the character code that we get back when we press the escape key on our keyboard. And now when I do that, when I press escape, I will quit. This quit breaks out of this repeat loop, and then I will come back to the menu. Now, the LEDs will be in the state they were last in. And so keep in mind that. But the loop will no longer be running. And, oh, sorry, I did that. Here's the Christmas colors. I'm doing the same thing inside the random colors. So if we look at the random, it's doing the same kind of thing. It's running what I was running before, but with a small delay. Now, I wanted this to be a little bit more exciting, so it's a little bit faster. So it's only 100 millisecond delay. So it flashes a little bit faster. And again, if I press escape, it'll all stop. And then the final version of the program, I'm getting, there we go. So there's one last version of the program does two things, because what you'll notice, again, this is for the new folks, you start to see the same thing. You notice this section of code that says, hey, look for a key, and I've got it here. 2. What could ultimately happen though is we might say, geez, I don't want to use a terminal. I want to use a button to end my process. So it would be better to obfuscate the details into a nice method that just says, hey, the user wants to quit. So that's what's going on in version 6. You'll see that there is a program called user quit. And this is going to return true or false to say, hey, the user pressed the escape key. Now this is, I mentioned earlier, one of the things I do like about Spin 2 is that it brings over the ternary operator from C and other languages. So this is saying, is there a key pressed and is it escape? If it is, we return true, otherwise we return false. So within the method, I say if user quit, quit, and it exits out. Now, if in another program, I want to quit with a push button, I can change this code to the push button and I don't have to manipulate any of these because they have this generic call to a function that says, hey, did the user quit? And just for fun, I added one last feature to this. This is a little, hopefully you like this one a little better, Roy. The twinkle. So if we run twinkle, what this does, if you look at it, you can see the thing grew, press twinkle. It's a little bit more exciting. What it does, if you analyze the twinkle routine, is that it will randomize a level between 3 and 31. And then it will stick that into the red, green, and blue chip so that it's white. We're twinkling white. I made that decision. And then we set that out to the channels. And now that I'm seeing this, somebody tell me what I could have done differently with this. All right, we're all getting tired, so I'll tell you. I could have used set all. I don't have to set the individual channels because I'm setting them all. Oh no, I take it back. So, never mind, take it back. I am setting them individually. That's how it twinkles. So, and then a quick wait.
I didn't see a problem. That's why I didn't.
Yeah,
say
no,
anything.
you're right. No, I'm tired. I tried to say we're tired. I'm tired. Anyway, we've gone on far longer than I expected, and I will not talk anymore except to answer your questions.
I just want to comment to say it was a very good presentation. Thank you.
Thank
Even
you.
though I am the expert or whatever you like to say, it was still.
You are an
informative.
expert.
It was still informative because I'm new to Spin 2.
Okay. Well, I think I think you'll see. It'll be interesting. We'll talk later about it, but I think you'll see that it's getting influence from more mature languages, and it's doing some really nice things. And it's shockingly fast for an interpreted language.
Yeah, well, Chip modified the hardware to make Spin faster as he was writing Spin, which was really interesting to watch.
It is a different process than, say, Microchip or Motorola or somebody else that are building chips. So look,
John,
Paul Willoughby is my kind of guy. He looks like he's wearing magnifiers on his head, and he's got LEDs around. This is a cool dude.
I've got 2 magnifiers on myself.
Oh, excellent.
So, John, I have one really dumb question.
There are no dumb questions.
Okay, if you scroll up where you have the constant for true and false.
Uh-huh.
So I guess I'm just a little confused by you have true is on or off, or we're saying it could be, it can only have those 2 values?
No, thank you for pointing this out, because this is another feature of Spin that these are called enumerated constants. And so what happens is you start with a value here, and then you have a list of constant names. Now, in this case, I'm only using 2. This first one will take on this value. The next one will, unless you modify it, and you can modify it. I don't tend to do that, but you can. It adds 1. So true, now this is something that I know internally, true is equal to -1 inside the propeller because it's all bits are set to 1. I think I talked about this in my last presentation. We talk about 2's complement, the way binary numbers are stored, but it turns out that in a 2's complement number, -1 is all the bits set. And so true is -1 because we want all the bits on. And so I'm calling that on. Well, if you add 1 to -1, that's 0, and that's off. So that's what's going on here, is that we have this is -1 and this is 0, and I'm giving them additional names, on and off. Now here's another way. This is 0, and so that's 0. And now in this case, this is 1. And so you have to be a little bit more careful how you use this version. And most programmers, and I'll ask my friend Roy to chime in because I think he'll agree with this. We know that false is going to be 0. So if it's not false, it's not 0. So any non-zero number we treat as true.
Yeah, that's typically true. It's just a special case for spin because it's designed around microcontrollers where it makes true be -1 so that it has all the bits on, because then you can assign it to a pin. On the P1, you would assign it to like out A or out B, and it would set all of the pins to one value.
Well, you could do that. You could actually do that even on the P2. So for example, now I'm going to use magic numbers, but if I said, if I said pin high, I am tired. So if I say 56, add pins 4 on, this would set pins 56, 57, 58, and 59 to 1.
Yeah, exactly.
So there are reasons for the way that I defined those. I'm sorry, I didn't see who asked the question, but that structure that you saw there, that is called enumerated constants. So if you look that up in the documentation, you'll see lots of other examples. And again, you can change the enumeration values, and you can even make 2 values have this, 2 names in the enumerated list have the same value. Again, I try not to get too clever with my programs. I want things to be really obvious, but I recognize that now that you've asked that maybe not was so obvious. But true and false are values that are defined. I'm just giving these things values, on and off and no and yes.
Okay. All right. Thank you very much for answering that.
You're welcome.
And then I had one other quick question. I saw you mention this on the forum the other day. I think at the end of your main, you had the repeat count loop.
Mm-hmm.
And I think in the forum you mentioned that was for in case the processor ever reboots. I'm just trying to get my head around when that piece of code would ever be executed.
You're seeing this right here.
Yeah.
It usually doesn't. Well, in this case it will, but in most of the cases, for example, if we look up here, I took it out, but most of the time I don't take it out. What happens is that when I will confess, I don't know all the details of the P2 yet, but I've done a little bit more with this on the P1. When the P1 sets up spin, it sets up this a stack so that, for example, when we call setup, what's going on is that we have to push an address onto the stack that tells setup where to go back to. And if we had arguments to pass along in there, and if setup took parameters, then those things have to go along on the stack as well. Well, in main, it's the first thing. It's not being called. And so what happens is in the P1, again, I don't know what the P2 does. I'll have to investigate, but the P1 sets it up so that if you hit the end of a method, like this one here, it does an automatic return. Well, main has nowhere to go. It was the first method. And so that can cause, at least the Propeller 1, I'm not sure what happens with the Propeller 2, but it causes the Propeller 1 to reboot. And you might not want that. So if you stick this little repeat wait count loop in there, it just holds it right there and it's in limbo until you do a manual reset. Again, it's just one of my habits that I do. Now,
Yeah,
again,
now
this is...
Yeah, go ahead. Oh, no, I was just saying, no, I appreciate it. It's great to learn all these best practices. And I had a great time tonight, so I really appreciate you doing this.
My pleasure. Thank you for joining in. I'm so, Roy,
Yeah,
were you going
I
to
learned
chime
a
in?
lot.
Thank you.
What was I supposed to chime in on? Sorry.
Well, I thought you were saying something. Maybe there was more details I missed about the call return stack stuff and with main.
Honestly, I'm not sure what happens on P2 with spin 2 at the end, but I'm pretty sure in FlexProp, Eric made it do like a infinite loop or something.
Oh, so he builds that in there. That's okay. That works out really nicely. So I'm manually putting it in. And you'll see, I've written some commercial programs and I put a little note in there that just to force it. So, normally I don't want this loop to exit, but if it did, what I will do just to make sure that it does what I want it to, I'll put reboot in there. Now, I guess reboot is not a P2 keyword. I'll have to ask Chip about that. In the P1, you can force a reboot with the reboot keyword. And because if I got out of my main loop, something went haywire.
Actually, I may be wrong. I'd have to double check, but I think it might actually be a cog stop instead of the infinite loop at the end that he inserts. It's a single instruction, basically.
Okay. Yeah, I'll have to. Well, I think Brian is working on a spin disassembler. I think Chip now is too. It'd be interesting to look at, this standard P2 code that's been compiled with Propeller tool and disassemble it to see what happens there at the end.
Yeah. Sure, Chip stuck something in there.
Probably.
John, you've made us all more capable this evening. And I feel like...
Forewarn you out.
No, I could use the driver now. And before I didn't have a chance, but I feel like I can modify some of the top level spin code to do what I want to do.
Well, that's it. And that's the point is that again, if you're just doing the basics, you're following kind of the guidelines, you're not going to hurt anything. So play, see what color combinations work. I mean, we're, colorblind people, this is not so fun, but those of us that can see colors, you sometimes will think, oh, geez, hey, if I mix these two colors, I should get this. Well, you find out that LEDs are sometimes tricky. And let me just say one final thing for those of you who hung in this long on LEDs. You'll notice that I supply, there's this thing called gamma that is in the LED thing. The reason for this is that LEDs, we have normally we will drive an LED with a number between 0 and 255, 0 being 0%, 255 being 100%. And the problem, though, is that the brightness level is not linear, even though we're getting a linear value. The LED brightness gets very bright at the beginning and then has a flatter curve towards the top. So what people have done is created a gamma curve table where you take the brightness level you want and you run it into this table, and this gives you the LED control level that should give you that apparent brightness. So you can try this, and now that you know how to do repeat loops, do repeat 0 to 255 and put it into a pixel. If you're running one pixel, you're not going to hurt anything, and watch the color go up and down. And then you'll notice it'll get very bright very fast, and then use the gamma curve. And then you'll notice it'll be a nicer curve. And I have to use this a lot because my client, Steve Wang, we do lots of throbbing LED stuff on those displays. And without the gamma curve, it wouldn't look nearly as nice as it does. So again, this is one of those play things. Art is subjective and LEDs are art. So have fun.
And John, next week, which part will we be adding to this, the LCD or the encoder?
I think we should, well, we can do the LCD if people like. I was going to go the encoder because it's kind of, discrete and we don't have to hook up too much. It's really easy. We can use it through the terminal. And between now and then, maybe I can get a hold of Eric Smith and figure out how we can help the FlexProp people have nice terminal access like we have through PST.
Great. Got a lot to look forward
John?
to.
Yes.
John,
Yes.
I followed along with all of these demos, and they all worked with FlexProp,
Good.
including the terminal. I don't know if the GUI version of FlexProp does this, but the command line wanted to use an uppercase T to get into terminal mode. It emulates PST.
Oh,
So
excellent.
everything worked fine.
Oh, thank you, David.
Thanks,
Fantastic.
David, for checking that out.
Yeah, I because you'd mentioned in the forums, I was thinking of you because I knew that you wanted to use it, and I just want people to have fun with code. I don't care what compiler anybody uses, just have fun. But I'm glad that it is working for you.
Yeah, I remember Eric added the PST emulation thing option, or somebody
fantastic.
added it for him. So yeah, you can just edit the GUI to have that / command on your load command,
Right.
and it'll do the same thing.
Oh, excellent. That's good news. Okay. Yeah, because I was playing last night and I was trying to figure out ANSI escape codes, and then I thought, okay, I've had a long day already and I can't figure this out. I can get some help from Eric perhaps, but that's good news. Anyway, thank you, David.
Okay, John.
About that exact question. Yeah.
Go ahead, Gerald.
So David, would you do me a favor, please? And in that thread in the forums, would you kind of put a little note in there saying, hey, if you're using FlexProp, here's how you can use John's, fancy terminal stuff?
Okay.
Thank you.
Okay, I have a question. Okay, here's the problem I'm having. I am like 99% done with porting the Peanut code, which does all the really cool debug stuff. I'm now starting to get into message crackers and things, and actually running through Chip's drawing code. But when I try to load a Blink program that's going to just say hello world over and over again, that's written in Spin, and I load that binary and run it from my terminal, nothing. It's completely unresponsive. I can load programs that are written in FlexC and they will run. I've got one running right now. I can access Lisp. I can access Taco's fourth. I can connect to Taco's fourth at 12 megabits, supposedly. I don't know if it's real or not. I can upload at 3 megabits. I can change COM port speed. I'm doing a lot of stuff in the GUI with creating dialog boxes and menus and pull downs so that I can fuss around with serial port parameters and starting on the command routing so I can have debug windows that are part of Chip's GUI code, where at least I'm clearing the screen and getting an ellipse with a oscilloscope graticule for the XY plot and stuff. But nothing, absolutely nothing is coming back when I run a Spin program that appears to run in Peanut. It is like totally blank, and it's not my code that's failing to call readcom. It is like Spin programs are just simply deaf, even when I change port speeds. Any ideas? I'll be more than happy to share my screen and walk through what I'm doing here to get this, so I can start.
I think we're going way past the beginner's lesson of this. You should probably contact Chip, Gerald, and talk to him about it, because the latest version of Propeller tool that I'm using has the latest compiler from Peanut. It doesn't have the debug stuff enabled yet, but it's the same compiler just wrapped in a Windows thing. So, what you're doing is way beyond what the rest of us are here. So I think it'd be better to have an offline conversation with Chip.
Yeah, let's take it up on Tuesday when we have his attention.
Okay, next time. Let me just throw the question then at John. The question is, are you using any other terminal modes? Because you mentioned like DMX stuff and irrigation stuff. Have you done anything with proprietary communications protocol where you've had to write your own serial driver from scratch that's running on a PC or something as far as talking to Spin programs? Have you done anything in that sense in terms of how do I make a Spin program? Have you yourself done anything? Because I know you mentioned DMX, and I'm familiar with lighting boards and things. And how that, that's usually like a custom protocol, and it's got 512 channels and things, and it's updating 60 times a second, you know, in terms of what's going to a lighting grid, like in a theater or something. I know how that works. That's a special proprietary, like RS 482 or 485 type thing. So I'm just wondering, you know, when you're doing that stuff, do you ever talk to the propeller that's doing these animated belts and things